The people who launch it will never arrive. That is not a flaw in the design. That is the design. Somewhere in the engineering archives of humanity's most ambitious Starship proposals, there is a vessel that requires 25 trillion miles to reach its destination. A journey so long that the crew who depart Earth will die of old age decades before the ship even reaches cruising speed. Their children will live and die aboard. Their grandchildren will do the same, and their great-great-great-great-great-grandchildren, people who have never breathed unfiltered air or felt gravity that wasn't spun into existence, will be the ones who finally see another star up close. We call it a generation ship, but that name doesn't come close to capturing what it actually is. This isn't a vessel, it's a civilization, a closed world hurtling through the void with no resupply, no backup, and no way home. Thousands of people, hundreds of years, every drop of water recycled, every breath of oxygen pulled from algae and plants that must never fail. Every child raised to operate machines their ancestors built, teaching knowledge no one can afford to forget, holding together a society that will fracture under the weight of isolation, boredom, and the crushing realization that no one aboard will ever see the mission succeed. And here is the part that should disturb you. We don't know if it's even possible. The engineering is brutal. The biology is uncertain. The psychology is catastrophic. But the distance is real. Proxima Centauri sits 4.24 light-years away, and if humanity is ever going to step foot on a world orbiting another star, someone is going to have to climb aboard a ship their great-grandchildren might survive. This is what it would actually take to cross the void, and why the humans who arrive may not be human anymore. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Light moves fast. This is not a metaphor or a figure of speech. Light is the fastest thing in the universe. Nothing travels faster. Not spaceships, not particles, not information itself. Light moves at about 186,000 miles per second. That is fast enough to circle the entire planet Earth 7.5 times in 1 second. If you could somehow hitch a ride on a beam of light leaving the surface of the sun right now, you would reach Earth in about 8 minutes. You would pass the moon in just over a second. You would blow past Mars in a few minutes, Jupiter in under an hour, and Pluto, the farthest dwarf planet, still clinging to the edge of our solar system, in about 5.5 hours. Light is fast, and yet, even at that unimaginable speed, reaching the nearest star to our sun would still take more than 4 years. That star is called Proxima Centauri. It sits roughly 24 light-years away from us. A light-year, by the way, is not a measure of time, it is a measure of distance. It is how far light travels in 1 full year, moving at that blistering 186,000 miles per second, without pause, without slowing down, without hitting traffic. 1 light year works out to about 6 trillion miles. Do the math, and Proxima Centauri is sitting roughly 25 trillion miles away from the chair you are in right now. That is the closest star we have, the next door neighbor in cosmic terms. And it is 25 trillion miles away. Let's put that in perspective, because numbers that large tend to stop meaning anything to the human brain. The distance from the Earth to the Sun is about 93 million miles. Astronomers call that distance 1 astronomical unit, or AU for short. It is a useful yardstick for measuring things inside our solar system. Proxima Centauri is about 272,000 astronomical units away. That means if you lined up the distance from the Earth to the Sun 272,000 times in a row, you would finally reach the edge of the Alpha Centauri system where Proxima sits. Pluto, on the far edge of our neighborhood, orbits at about 40 AU. The Voyager 1 spacecraft, which launched in 1977 and is currently the most distant human-made object in existence, is sitting at roughly 160 AU from Earth. It has been traveling for nearly 50 years, and it has covered less than 0.1% of the distance to Proxima Centauri. Voyager 1 is moving at about 38,000 miles per hour. That is faster than any crewed spacecraft has ever traveled. It is hauling through the void at a speed that would get you from New York to Los Angeles in under 5 minutes. And at that speed, it would take Voyager roughly 75,000 years to reach Proxima Centauri. 75,000 years. That is longer than all of recorded human history. That is longer than agriculture, longer than cities, longer than written language. When Voyager finally crosses the distance to Proxima Centauri, assuming it does not hit anything along the way, humans will have evolved into something unrecognizable or gone extinct entirely. The Sun itself will have drifted to a different position in the galaxy. The constellations we see tonight will have rearranged. Voyager will still be coasting silently through the dark, carrying a golden record with greetings in 55 languages, a map showing Earth's location, and a recording of Chuck Berry's Johnny B. Good, a postcard from a species that will have been dead for tens of thousands of years. This is the problem. This is why interstellar travel is not a matter of building a better rocket or finding a bigger fuel tank. It is not an engineering challenge in the normal sense, where you identify a bottleneck, throw resources at it, and eventually break through. The bottleneck here is physics itself. And physics, unlike budgets or schedules or public interest, does not negotiate. Chemical rockets, the kind that took humans to the moon and currently launch satellites into orbit, work by burning fuel and expelling the exhaust out the back at high speed. The faster the exhaust, the more thrust you get. The problem is that chemical reactions have a speed limit. The exhaust from even the most efficient chemical rocket cannot exceed a certain velocity, which means the spacecraft itself cannot accelerate past a certain point without carrying absurd amounts of fuel. And fuel has mass. The more fuel you carry, the heavier your spacecraft gets, which means you need even more fuel to accelerate that additional mass, which makes the spacecraft heavier still. You end up in a trap where most of your rocket's energy is spent just moving the fuel rather than the payload. The numbers spiral out of control almost immediately. Ion engines, which NASA has used on deep space probes like Dawn and the upcoming Psyche mission, are more efficient. They work by ionizing a propellant, usually xenon gas, and accelerating the charged particles using electric fields. The exhaust velocity is much higher than a chemical rocket, which means you get more thrust per kilogram of fuel. The trade-off is that ion engines produce very little thrust overall. They accelerate slowly. A spacecraft powered by an ion drive can eventually reach higher speeds than a chemical rocket, but it takes years of continuous thrusting to get there. And even then, the top speeds we are talking about are still measured in tens of kilometers per second, nowhere near the kinds of velocities you would need to make interstellar travel practical within a human lifetime. Let's do the math. If you wanted to reach Proxima Centauri in, say, 50 years, you would need to travel at about 1/10 the speed of light. That works out to roughly 18,600 miles per second. For comparison, Voyager 1 is moving at about 5 miles per second. You would need to go nearly 2,000 times faster than the fastest object humanity has ever launched, and you would not just need to accelerate to that speed. You would need to carry enough fuel to slow down once you got there, unless your plan is to scream past your destination at a significant fraction of light speed and wave as you go by. To decelerate, you need to fire your engines in the opposite direction for just as long as you spent speeding up, which means you need to carry at least twice as much fuel as you thought. Except you also have to accelerate that deceleration fuel at the start of the trip, which means even more fuel, which means more mass, which means more fuel, and once again the numbers explode into absurdity. There are theoretical propulsion systems that might, in principle, get around some of these problems. Nuclear pulse propulsion, for example, involves detonating small nuclear bombs behind a spacecraft and riding the shockwave. The idea was seriously studied during Project Orion in the 1950s and 60s, and the physics actually works. You could, in theory, reach a few % of light speed using this method. The engineering challenges are, to put it mildly, non-trivial. You would need to carry thousands of nuclear devices, each one precisely timed and positioned, and your spacecraft would need to survive the repeated blasts without shaking itself apart. You would also need to launch this thing from Earth, which means convincing the international community that launching a spaceship powered by nuclear explosions is a good idea. That has not happened yet. Antimatter propulsion is even more exotic. When matter and antimatter meet, they annihilate each other and convert their entire mass into energy, according to Einstein's famous equation. The energy release is orders of magnitude greater than any chemical or nuclear reaction. If you could somehow harvest and store antimatter and then use it as fuel, you could theoretically reach speeds close to the speed of light. The problem is that antimatter is extremely rare in nature, and producing it artificially is staggeringly expensive. Current estimates put the cost of producing 1 gram of antimatter at somewhere around $62 trillion, a single gram. A trip to Proxima Centauri would require tons of the stuff. And even if you could afford it, storing antimatter without letting it touch any normal matter and explode is an unsolved problem. Scientists can trap tiny amounts of antimatter using magnetic fields for fractions of a second in laboratory conditions. Scaling that up to an interstellar fuel tank is science fiction in the truest sense. We do not know if it is possible. Solar sails are another idea. Instead of carrying fuel, you unfurl an enormous mirror and let the pressure of sunlight push you forward. The acceleration is tiny, but it is continuous, and you do not need to carry propellant. The Planetary Society successfully tested this concept with their LightSail 2 spacecraft, which used photons from the Sun to adjust its orbit. For interstellar distances, though, sunlight gets weaker the farther you go. Once you are beyond the outer solar system, the pressure drops off so dramatically that a solar sail becomes nearly useless. Some proposals suggest using powerful lasers on Earth or in orbit to push a solar sail up to high speeds, but now you are talking about building laser arrays with power outputs equivalent to entire nations and keeping them focused on a tiny reflective sail millions or billions of miles away for years. Again, possible in theory, not something anyone knows how to build today. Breakthrough Starshot, a research initiative funded by billionaire Yuri Milner, is exploring exactly this idea. The plan is to send tiny spacecraft, each weighing only a few grams, to Alpha Centauri using ground-based lasers. The spacecraft would be little more than a computer chip attached to a light sail. If everything works perfectly, the lasers could accelerate the craft to about 20% the speed of light, which would get them to Proxima Centauri in roughly 20 years. Even at that scale, the engineering problems are borderline ridiculous. The laser array would need to output about 100 gigawatts of power. For context, that is roughly the total power output of 100 nuclear reactors. The sail would need to be incredibly thin and incredibly reflective, and it would need to survive being hit by a laser pulse powerful enough to vaporize almost anything. If the project works, and that is a very large if, the probes would zip past Proxima Centauri at a fifth of light speed, snap a few photos, and beam the data back to Earth. The signal would take another 24 years to arrive. By the time we see the pictures, the probes will be long gone, coasting into the dark on the far side of the star. They will not slow down, they will not orbit, they will not land. They are one-way scouts, and they weigh less than a smartphone. None of this gets a human being to another star. Not within a human lifetime, not within 10 lifetimes. The distances are simply too large, and the speeds we can achieve are simply too small. If you want to send people, actual living, breathing people, to another star system, you are forced into one of two options. Either you invent a propulsion system that bends or breaks the known laws of physics, or you accept that the journey is going to take longer than any single human will live, much longer. This is where the concept of a generation ship comes from. A generation ship is exactly what it sounds like. A spacecraft large enough and robust enough to support a population of human beings, not for years or decades, but for centuries, maybe longer. The people who launch the ship will not see the destination. Their children will not see it. Their grandchildren will not see it. Somewhere many generations down the line, distant descendants who were born in space, who have never set foot on a planet, who have only ever known the inside of a starship, will finally arrive at a new world, if everything goes right. The idea is not new. It has been floating around in science fiction since at least the 1920s. Robert Goddard, one of the pioneers of modern rocketry, mentioned it in some of his private notes. In 1929, a scientist named J.D. Burnell wrote a speculative essay describing massive space habitats that could carry humans across the stars over multiple generations. The term generation ship itself was popularized in the 1950s and 60s through stories by writers like Robert Heinlein, who wrote about a crew aboard a starship that had forgotten they were on a starship at all. The idea was that after enough generations, the knowledge of the mission would be lost, and the descendants would think the ship was the entire universe. That premise, incidentally, is not as far-fetched as it sounds. Human cultures forget things all the time. Languages die, technologies are lost, entire civilizations collapse, and their successors have no idea how their monuments were built. If you put a few thousand people inside a giant metal tube and send them into the void for 50 or 100 generations, there is no guarantee the knowledge of the mission survives intact. Maybe it does, maybe it does not. That is part of the problem. Let's be clear about what we are discussing here. A generation ship is not a rocket with a crew compartment. It is a self-contained world, a closed-loop biosphere capable of recycling air, water, and food indefinitely. It needs farms or some equivalent to produce food. It needs medical facilities to handle births, injuries, illnesses. It needs schools to educate children who will grow up to operate and maintain systems they did not design. It needs some form of government or social structure to keep order among people who will live their entire lives in confinement. It needs genetic diversity to prevent inbreeding over dozens of generations. It needs redundancy in every critical system, because if the water recycling plant breaks 200 years into a 1,000-year journey, there is no one to call for help. And it needs to be large enough that the people inside do not go insane from claustrophobia or social collapse before they reach their destination. The largest spacecraft humanity has ever built is the International Space Station. It weighs about 420 tons and has a habitable volume of roughly 13,700 cubic feet, about the size of a 6-bedroom house. A crew of 6 or 7 people live there for months at a time, but they rely on regular resupply missions from Earth. Food, water, spare parts, everything gets shipped up from the ground. The station is not self-sustaining. It is more like a research outpost at the South Pole. Isolated, yes, but not independent. A generation ship would need to be hundreds or thousands of times larger. It would need to support not 6 people, but thousands. It would need to do so not for 6 months, but for centuries. And it would need to do all of that with zero outside help. Nobody has ever built anything like that. Nobody has even come close. The engineering challenges are so enormous that most serious scientists treat generation ships as thought experiments rather than actual proposals. But thought experiments have a way of becoming real when the alternative is extinction or stagnation. If humanity ever decides it truly wants to reach another star, to set foot on a planet orbiting Proxima Centauri or any of the thousands of other stars scattered across the galaxy, a generation ship might be the only way to do it with current physics. That is the box we are in. The universe is unimaginably vast. Light itself, the fastest thing that exists, takes years to cross interstellar distances. Our rockets are slower than light by a factor of thousands. Unless something fundamental changes in our understanding of propulsion or space-time itself, any trip to another star becomes a multi-generational endeavor by default. So the question is not whether we can reach another star within a human lifetime. We cannot. The question is whether we can build a vessel capable of carrying human life across the void for long enough that someone, someday, many generations from now, steps onto alien soil, and if we can, whether we should. Because building the ship is only the beginning. Keeping the people inside it alive, sane, and functional across centuries of isolation is an entirely different problem. One that has nothing to do with rockets or fuel or distance, and everything to do with biology, psychology, and the fragile systems that keep human societies from tearing themselves apart. That is what happens when you try to turn a spaceship into a world. Building a spaceship is difficult. Building a world is something else entirely. And a generation ship, despite the name, is not really a ship at all. It is a world. A small one, yes. An artificial one, certainly. But a world nonetheless, complete with its own atmosphere, its own water cycle, its own food production, its own weather in a sense, and its own population of inhabitants who will be born inside it, live their entire lives inside it, and die inside it without ever setting foot on the planet their distant ancestors left behind. The engineering required to make that possible does not exist yet, not even close. Let's start with scale, because scale is where most people's intuition breaks down. When you hear the word spaceship, you probably picture something like the space shuttle, maybe the International Space Station if you are thinking big. Perhaps a science fiction vessel like the Starship Enterprise, if you are feeling generous. All of those are toys compared to what a generation ship would need to be. The International Space Station, the largest structure humans have ever assembled in space, weighs about 420 tons and has a pressurized volume of roughly 13,700 cubic feet. That is about the size of a 6-bedroom house. It supports a crew of 6 or 7 people for a few months at a time, and it does so only because cargo ships from Earth arrive every few weeks, carrying food, water, spare parts, and fresh supplies. The station is not self-sufficient. It is a research outpost, not a colony. A generation ship cannot rely on resupply missions. There is no ground control to call when something breaks. There is no rescue operation if things go wrong. The ship has to carry everything it will ever need for centuries, and it has to support not 6 people, but thousands. One design study frequently cited in the literature suggests a ship roughly 320 meters long and 224 meters in radius. To give you a sense of what that means, 320 meters is just over 1,000 feet. That is longer than 3 football fields laid end to end. The radius of 224 meters means the widest cross-section of the ship would be nearly 450 meters across, about a quarter of a mile. This is not a vehicle you park in a hangar. This is a structure you could see from space with the naked eye if you were anywhere near it. The same study estimates the ship would need at least 450 square meters of farmland just to feed the crew. That is a little over 4,800 square feet, roughly the size of a large suburban house, and that is the absolute minimum. Most realistic estimates suggest you would need significantly more agricultural space to account for crop failures, dietary variety, and the simple fact that farming in an enclosed metal tube hurtling through the void is going to be harder than farming on Earth. Another proposal, this one for a rotating habitat designed to house about 500 people, suggests a structure roughly 448 meters in diameter and 640 meters long. The estimated mass comes in at around 400,000 tons. To put that in perspective, the largest ship ever built on Earth, the oil tanker Seawise Giant, weighed about 260,000 tons when fully loaded. A generation ship would need to be half again as heavy as the largest seagoing vessel in history, and it would need to be assembled in space because there is no way to launch something that massive from the surface of a planet. You would need to mine asteroids for raw materials, smelt the ore in zero gravity, fabricate components in orbit, and then assemble the whole thing piece by piece over the course of years or decades. Nobody has done any of that yet, except in the most preliminary experimental sense. Now let's talk about why the ship needs to be so large. The answer is not just about carrying more people, though that is part of it. The real reason is that a generation ship needs to function as a closed-loop ecosystem. And ecosystems require space, a lot of space. You cannot cram 1,000 people into a tin can and expect them to survive for 200 years. They need room to grow food. They need room to recycle water and air. They need room to move around, to exercise, to raise children, to maintain their mental health. Human beings are not meant to live in closets. Put someone in solitary confinement for a few months and their brain starts to break. Now imagine asking entire families to live in close quarters for their entire lives, generation after generation, with no possibility of stepping outside. The ship has to be large enough that people do not feel like they are living in a prison, because if they do, the mission will fail long before the ship reaches its destination. This is where rotating habitats come in. If you have ever seen concept art of an O'Neill cylinder, you know what I am talking about. The idea was proposed by physicist Gerard O'Neill in 1976 as a way to create artificial gravity in space. Take a massive cylinder, seal both ends, spin it along its central axis, and centrifugal force pushes everything inside toward the outer wall. To the people living on that inner surface, it feels like gravity. Walk around, drop a ball, pour a glass of water, and everything behaves the way it does on Earth. The faster you spin the cylinder, the stronger the artificial gravity. The larger the radius, the slower you need to spin to achieve the same effect. A small cylinder spinning too fast makes people nauseous. A large cylinder spinning slowly feels perfectly normal. O'Neill's original designs were enormous, some with radii measured in kilometers, intended as permanent space colonies orbiting Earth or the Moon. A generation ship does not need to be quite that large, but it still needs to be big enough to create comfortable artificial gravity without spinning so fast that the Coriolis effect messes with your inner ear every time you move. The Coriolis effect, by the way, is what happens when you move inside a rotating reference frame. If you walk toward the center of a spinning cylinder, you feel a sideways force pushing you in the direction of the spin. If you walk away from the center, you feel a force in the opposite direction. On a small, fast-spinning habitat, that force is strong enough to make people feel sick. On a larger, slower spinning one, it is barely noticeable. Most studies suggest a minimum radius of about 100 meters to keep the Coriolis effect tolerable. Go smaller and you start making your crew ill. Go larger and you need more materials, more mass, more structural reinforcement, and more energy to spin the thing in the first place. Some generation ship designs avoid rotation altogether and instead use constant acceleration to simulate gravity. Accelerate at 1 g, about 9.8 meters per second squared, and the crew feels normal Earth gravity pushing them toward the back of the ship. The problem is that constant acceleration requires constant thrust, which requires fuel, and as we have already established, carrying enough fuel for an interstellar journey is somewhere between impractical and impossible with any propulsion system we currently have. Even if you solve the propulsion problem, you still need to flip the ship around halfway through the journey and decelerate at the same rate, or you will blow past your destination at a significant fraction of light speed. For a journey lasting centuries, constant acceleration is not realistic. Rotation is the only practical option, which means the ship needs to be cylindrical or ring-shaped, and it needs to be large. The structural challenges of building something like this are, to put it mildly, absurd. Start with the basic problem of holding the thing together. A rotating cylinder experiences immense centrifugal stress. The outer hull is constantly trying to fly apart. Every rivet, every weld, every structural beam has to withstand forces that would tear apart a conventional spacecraft. The materials need to be incredibly strong, incredibly light, and incredibly durable, because you cannot afford to have the hull fail 300 years into a 1,000-year journey. Steel is strong, but it is heavy. Aluminum is lighter, but it is not as strong. Titanium is both strong and relatively light, but it is expensive and difficult to work with. Composite materials like carbon fiber are even lighter and stronger, but they are brittle and can fail catastrophically under the wrong conditions. Some designs propose using a combination of all of these, layered in ways that distribute stress and provide redundancy so that if one layer cracks, the others hold. Then there is radiation. Space is full of it. Cosmic rays, high-energy particles streaming in from every direction, slamming into anything in their path. Solar radiation from the sun, or in the case of an interstellar journey, from whatever star you are approaching. Galactic cosmic rays that originate from supernovae and other violent events across the galaxy. On Earth, we are protected by a thick atmosphere and a planetary magnetic field that deflects or absorbs most of this radiation before it reaches the surface. In deep space, you have no such protection. A human being exposed to the radiation environment outside Earth's magnetosphere would start accumulating dangerous doses within weeks. Over months or years, the risk of cancer and other radiation-related illnesses climbs sharply. Over centuries, without shielding, the crew would be dead long before the ship reached its destination. Shielding against radiation is not simple. The most effective shield is mass. Pack enough material between the crew and the outside environment, and the radiation gets absorbed before it reaches them. Water works well. Rock works even better. Lead is excellent, but it is extremely heavy. Some generation ship designs propose using hollowed-out asteroids as the basis for the hull, specifically because asteroids provide ready-made radiation shielding in the form of solid rock. Mine out the interior, seal it, spin it, and you have a habitat that is naturally shielded from cosmic rays. The downside is that asteroids are not structurally uniform. They are full of cracks, voids, and weak points. Reinforcing an asteroid to withstand the stresses of rotation without fracturing is an engineering nightmare. Other designs propose using the ship's own water supply as shielding. Water is necessary for life support anyway, so why not store it in tanks lining the outer hull? It absorbs radiation, it provides structural mass, and it serves double duty as a resource. The problem is that water is heavy. A cubic meter of water weighs a ton. A ship carrying enough water to shield a population of 1,000 people for centuries would need hundreds or thousands of tons of it, and all of that mass has to be accelerated and decelerated along with the rest of the ship. Even so, some analyses estimate that with best-case shielding, the crew might still receive an annual radiation dose of around 100 to 200 millisieverts per person. For comparison, the average background radiation dose on Earth is about 2 to 3 millisieverts per year. A single chest X-ray is about 0.1 millisieverts. Astronauts on the International Space Station receive about 50 to 200 millisieverts per year, depending on solar activity. A generation ship crew would be living at the high end of that range for their entire lives, with no breaks, no rotations back to Earth, no escape. The long-term health effects are unknown because no one has ever been exposed to that level of radiation for that long. Then there is the problem of micrometeoroids. Space is not empty. It is full of tiny particles, most of them no larger than grains of sand, traveling at tens of kilometers per second. At those speeds, even a fleck of dust carries enough kinetic energy to punch through metal. The International Space Station gets hit by micrometeoroids regularly. Most impacts are harmless, just tiny pits in the hull, or scorch marks on solar panels. Occasionally, though, a larger particle punches through a radiator or cracks a window, and the crew has to patch it. On a generation ship traveling for centuries, the cumulative damage from micrometeoroid impacts would add up. The hull would be pockmarked with thousands or millions of tiny craters. Some would penetrate the outer layers. Some might breach the pressure seal. The ship needs to be designed with multiple redundant layers, so that even if the outer hull is compromised, the inner pressure vessel remains intact. It also needs self-healing materials, or a crew capable of constantly patching holes, which brings us to another problem: repair. Everything breaks eventually. Electronics fail, seals crack, bearings wear out, pipes corrode. A spacecraft designed to last a few years can get away with some amount of planned obsolescence. A generation ship needs to last centuries, and it needs to do so with no possibility of ordering replacement parts from Earth. Every critical system has to be repairable using only materials and tools available on the ship. That means the crew needs to be able to manufacture replacement components from scratch. They need machine shops, 3D printers, chemical synthesis labs, and a comprehensive library of technical knowledge covering every system on the ship. They need raw materials to work with, which means the ship has to carry stockpiles of metals, plastics, ceramics, and other supplies, or it needs to recycle old components so efficiently that nothing is ever truly lost. Some designs propose mining asteroids along the way for raw materials, but that requires the ship to slow down, rendezvous with an asteroid, extract useful material, and then accelerate again. Every time you do that, you add years or decades to the journey. One analysis of long-duration reliability estimated that for a ship with about 1,000 critical components, the probability of all of them surviving without failure for 10 years drops to around 0.5%. That is not a typo. 0.005%, essentially zero. The implication is that unless every single system is designed with extreme redundancy and repairability, the ship will fail long before it reaches its destination. You cannot just build it and hope for the best. You have to assume that everything will break and plan accordingly. Now let's talk about power, because without power, everything else is irrelevant. A generation ship needs energy to run life support, to spin the habitat, to power the farms, to purify water, to operate computers and communication systems, to maintain lighting, to run repair equipment, and to do 1,000 other things that keep the crew alive. And it needs to do all of that for centuries without access to an external power source. Solar panels work near the sun, but once you leave the solar system, sunlight fades to nothing. At the distance of Proxima Centauri, the sun is just another star in the sky, far too dim to provide meaningful energy. Chemical batteries are out of the question. Even the best batteries degrade over time, and none would last more than a few decades. Fossil fuels are absurd for obvious reasons. That leaves nuclear power or something more exotic. Fission reactors, the kind currently used in nuclear submarines and some spacecraft, could in theory provide power for decades. Uranium-235 or plutonium-239, the usual fuels, have half-lives measured in hundreds of thousands or millions of years, so the fuel itself would not decay significantly over the course of the journey. The problem is that reactors are complex machines with moving parts, cooling systems, control rods, and all sorts of components that wear out. Terrestrial nuclear reactors are refueled and overhauled every few years. A generation ship reactor would need to run continuously for centuries with only onboard maintenance. Some designs propose using multiple smaller reactors so that if one fails, the others can take over, but that adds mass and complexity. Fusion reactors are the more attractive option, at least on paper. Fusion, the process that powers the sun, fuses light atomic nuclei, usually hydrogen isotopes, into heavier ones and releases enormous amounts of energy. The fuel, deuterium and tritium, can be harvested from water and lithium, both of which could be carried in relatively small quantities. A fusion reactor produces no long-lived radioactive waste, and the energy output per kilogram of fuel is orders of magnitude higher than fission. The problem is that we do not have working fusion reactors yet, not practical ones. Experimental reactors like ITER are still under construction, and even if they succeed, they will be massive, expensive, and finicky. Scaling fusion down to a size and reliability suitable for a generation ship is a problem that might be solved in the next few decades, or it might not, nobody knows. Some more speculative designs propose using hypothetical power sources that do not exist yet. Antimatter reactors, for example, or energy harvested from quantum vacuum fluctuations, or even more exotic ideas involving dark matter. These are not serious proposals, they are placeholders, ways of saying we need something better than what we have now, and we hope future physics will provide it. Maybe it will, maybe it will not. Assuming you solve the power problem, you still need to deal with heat. Every system on the ship generates waste heat. Reactors produce heat, electronics produce heat, Human bodies produce heat. In space, getting rid of heat is hard because there is no air to carry it away. The only option is radiation, which is slow. The ship needs massive radiators, probably extending from the hull like fins, to dump waste heat into space. If the radiators fail or get damaged, the interior temperature climbs, systems overheat, and people start dying. This is another critical system that has to work flawlessly for centuries. The picture that emerges from all of this is not a starship in any traditional sense. It is a mobile habitat, a tiny engineered world, spinning slowly through the void, carrying a fragile population of human beings who have no choice but to trust that the engineers who built their home got everything right, that the hull will hold, that the reactors will keep running, that the farms will keep producing food, that the water recyclers will keep recycling, that the air scrubbers will keep scrubbing, that the next generation will know how to fix what breaks, that the social order will hold together, that the mission will not be forgotten. All of that depends on what happens inside the ship, inside the closed-loop systems that have to sustain life without pause, without failure, without resupply, for longer than most civilizations have ever lasted. And that is where the engineering problem stops being about steel and starts being about soil. The ship is built, the hull is sealed, the reactors are humming, the crew is aboard, strapped into acceleration couches or standing in the observation bay watching Earth shrink behind them. The engines fire, the journey begins. And within 72 hours, if the life support systems are not functioning perfectly, everyone on board will be dead. Not from a reactor meltdown or a hull breach or a collision with an asteroid. From suffocation, from dehydration, from the simple fact that human beings are extraordinarily fragile machines that require very specific inputs to keep running, and if any one of those inputs stops flowing, the machine breaks down fast. This is the part most people do not think about when they picture a generation ship gliding elegantly through the stars. They see the vessel from the outside, rotating slowly against the backdrop of space, lights glowing through viewports, a tiny jewel of human ambition drifting through the void. What they do not see is the plumbing, the air scrubbers, the algae tanks, the waste processors, the hydroponic farms, the constant, unglamorous, life or death struggle to keep the internal chemistry of a closed metal tube balanced within the narrow range that allows human survival. Because that is what a generation ship is, at its core. Not a spaceship, not a habitat, a closed-loop ecosystem, a terrarium. And if the terrarium tips out of balance, everyone inside dies. Start with air, because air is where most people die first. A human being can survive weeks without food, days without water, but only minutes without oxygen. The air you are breathing right now is about 21% oxygen, 78% nitrogen, and 1% trace gases, including carbon dioxide, argon, water vapor, and a few others. That mix is not arbitrary. It is the result of billions of years of planetary evolution, stabilized by a biosphere that produces and consumes gases in a delicate equilibrium. Plants take in carbon dioxide and release oxygen. Animals take in oxygen and release carbon dioxide. Bacteria break down organic matter and release nitrogen. The ocean absorbs carbon dioxide and releases oxygen. The atmosphere mixes it all together. The result is breathable air, maintained automatically by an entire planet working as a single system. A generation ship does not have a planet. It has a few thousand cubic meters of pressurized volume, a population of humans exhaling carbon dioxide, and a life support system that has to replicate the work of an entire biosphere using machines and biology crammed into a space smaller than a shopping mall. Let's do the math. An average adult human exhales roughly 200 milliliters of carbon dioxide with every breath. At a resting breathing rate of about 12 to 20 breaths per minute, that works out to roughly 200 liters of carbon dioxide per person per day. If you have 1,000 people on board, the ship's atmosphere gains 200,000 liters of carbon dioxide every 24 hours. Carbon dioxide is not immediately toxic. It is a normal component of air. But if the concentration climbs above about 1%, people start feeling drowsy and sluggish. At 3%, you get headaches and impaired decision-making. At 5%, you are in serious danger. At 10%, you lose consciousness within minutes and die shortly after. The ship's life support system has to remove carbon dioxide as fast as the crew produces it, continuously, without pause, for centuries. On Earth, plants do most of that work. They pull carbon dioxide out of the air during photosynthesis, split it into carbon and oxygen, use the carbon to build sugars and cellulose, and release the oxygen back into the atmosphere. A single mature tree absorbs about 20 to 50 kilograms of carbon dioxide per year. If you did the math, you would need somewhere between 10 and 20 trees per person to balance the carbon dioxide output. For a crew of 1,000, that is 10,000 to 20,000 trees. Trees take up space, a lot of space. You cannot pack 10,000 trees into a generation ship. You do not have the volume, you do not have the soil, and you do not have the water to keep them alive. So instead, you use something more efficient, algae, specifically microalgae like chlorella or spirulina. These are single-celled organisms that photosynthesize just like plants, but they grow much faster and pack far more biomass into a given volume. 1 liter of dense algae culture can absorb as much carbon dioxide per day as several square meters of forest. Algae also produce oxygen at a high rate, doubling or tripling their mass every few days under the right conditions. NASA has been studying algae-based life support since the 1950s, and some of the space station prototypes in the 1980s and 90s used algae tanks as part of their closed-loop systems. The idea is simple. Pump carbon dioxide-rich air through a tank full of algae suspended in water, shine bright lights on them to simulate sunlight, and the algae consume the carbon dioxide and release oxygen. Harvest the algae periodically, dry them out, and you have a protein-rich biomass that can be processed into food or fertilizer. Clean, efficient, self-sustaining. In theory. In practice, algae are finicky. They need precise lighting, the right temperature, the right pH, the right concentration of nutrients in the water. If the light is too dim, they stop growing. If it is too bright, they bleach and die. If the temperature drops, their metabolism slows. If it climbs too high, they cook. If the water gets contaminated with the wrong bacteria or fungi, the whole culture crashes and you are left with a tank of rotting sludge. Algae-based life support systems have been tested extensively in laboratory conditions, and they work, but they require constant monitoring and adjustment. A human operator has to check the tanks daily, measure the oxygen and carbon dioxide levels, adjust the nutrient mix, harvest the biomass, clean the filters, and replace the lights when they burn out. On a generation ship, that work has to be done every single day for centuries, and the people doing it need to be trained well enough that they do not make mistakes that kill everyone on board. Some generation ship designs skip the biological approach entirely and rely on chemical scrubbers, the same technology used on submarines and the International Space Station. Lithium hydroxide canisters, for example, absorb carbon dioxide from the air through a chemical reaction. Breathe into a sealed room with a lithium hydroxide scrubber, and the air stays breathable for hours or days depending on the size of the canister. The problem is that lithium hydroxide is a consumable. Once it has absorbed all the carbon dioxide it can hold, it is spent. You have to replace it with a fresh canister and either store the used one or regenerate it, which requires heating it to high temperatures to drive off the carbon dioxide. That takes energy and equipment. On a submarine, you carry a stockpile of canisters and replace them as needed. On the International Space Station, you carry some canisters for emergencies, but most of the carbon dioxide removal is handled by a system called the Carbon Dioxide Removal Assembly, which uses a regenerable amine solution to scrub the air. The amine absorbs carbon dioxide, then gets pumped into a separate chamber where it is heated, releasing the carbon dioxide into space and regenerating the amine for reuse. That works in low Earth orbit where you can vent waste gases overboard. On a generation ship, you cannot afford to throw anything away. Every atom matters, so the carbon dioxide has to be captured, stored, and ideally converted back into something useful. Some designs propose using the Sabatier reaction, a chemical process that combines carbon dioxide with hydrogen to produce methane and water. The methane can be burned as fuel or vented if necessary, and the water goes back into the ship's supply. The hydrogen comes from electrolysis, splitting water into hydrogen and oxygen using electricity. The oxygen gets pumped back into the air. The hydrogen goes to the Sabatier reactor. The whole system runs in a loop, using energy from the ship's reactors to turn carbon dioxide and water into breathable oxygen. The International Space Station uses a version of this system, and it works. But again, it requires energy, maintenance, and backup systems in case something breaks. Now let's talk about oxygen, because removing carbon dioxide is only half the problem. You also have to replace the oxygen that people consume. A resting adult uses about 550 liters of oxygen per day. For a crew of 1,000, that is 550,000 liters per day, or roughly 19,500 cubic meters per year. Oxygen is not a trace gas. It makes up a fifth of the atmosphere by volume. If your oxygen production stops, the concentration in the air starts dropping within hours. The crew gets tired, then dizzy, then they pass out, then they die. Oxygen production has to be continuous and reliable. Electrolysis is the most straightforward method. Run an electric current through water, and it splits into hydrogen and oxygen gas. The oxygen gets pumped into the air. The hydrogen gets stored or used in the Sabatier reaction. The process is simple, well understood, and reliable. The catch is that it requires a lot of water and a lot of electricity. If you are producing 550,000 liters of oxygen per day for 1,000 people, you are splitting roughly 700 kilograms of water per day. Over a year, that is more than 255 tons. Over a century, that is 25,000 tons. You cannot carry that much water just for oxygen production. The water has to come from somewhere else in the loop, from the crew's waste, from the moisture they exhale, from the condensation on the walls. Every drop has to be captured, purified, and fed back into the system. Nothing can be lost. This brings us to water, because water is the most critical resource on the ship after air. A human being can survive a few days without water, maybe a week if they are lucky. After that, the kidneys shut down, the blood thickens, and the brain stops functioning. Water is also heavy. A liter of water weighs a kilogram. A person needs about 2 to 3 liters of drinking water per day, plus more for cooking, hygiene, and agriculture. Call it 50 liters per person per day when you account for everything. For a crew of 1,000, that is 50,000 liters per day, or 50 tons. Over a year, 18,250 tons. A generation ship cannot carry that much water for the entire journey. It has to recycle every single drop. The International Space Station recycles about 90% of the water on board. Urine, sweat, condensation from the air, wastewater from hygiene, all of it gets collected, filtered, and purified back into drinking water. The purification system uses a combination of filtration, distillation, and chemical treatment to remove contaminants, and the resulting water is cleaner than most tap water on Earth. Astronauts joke that today's coffee is tomorrow's coffee, which is technically true. The system works, but it is not perfect. 10% of the water is lost in the process, locked up in solid waste or vented as vapor. On the space station, that loss is acceptable because cargo ships arrive every few months with fresh water. On a generation ship, there are no cargo ships. A 10% loss over centuries means the ship's water supply slowly shrinks until there is not enough left to sustain the crew. The recycling efficiency has to be much closer to 100%. Some estimates suggest 98 or 99% recovery, which sounds good until you do the math. Even a 1% loss per cycle means the water supply drops by half every 70 cycles or so. If a cycle is a year, that is 70 years. If the journey lasts 500 years, the crew runs out of water long before they arrive. So the ship needs a closed water cycle with near-perfect efficiency. That means capturing every drop of moisture from the air, every bit of liquid waste, every molecule of water vapor exhaled by the crew or transpired by plants. It means designing dehumidifiers that pull water out of the air continuously. It means treating urine not as waste, but as a resource. It means recovering water from feces, which on Earth sounds disgusting, but on a generation ship is a necessity. Some systems propose freeze-drying solid waste to extract the remaining moisture, then incinerating or compressing the dried material into inert blocks that can be stored or used as fertilizer. Other systems use biological processes, composting the waste with bacteria and fungi to break it down into simpler compounds while capturing the water released during decomposition. Either way, the goal is the same: get the water back, always. The plants help. A generation ship will likely rely heavily on hydroponics or aeroponics for food production, and those systems are essentially water recycling loops already. Hydroponics means growing plants in nutrient-rich water instead of soil. The roots dangle in the water, absorbing nutrients and oxygen, and the plants grow faster than they would in dirt because they do not have to waste energy searching for food. The water circulates through the system, gets filtered, gets re-enriched with nutrients, and circulates again. Some of the water is lost to evaporation and transpiration, but that moisture can be captured by dehumidifiers and fed back into the loop. In principle, a well-designed hydroponic system can recycle more than 95% of its water. The challenge is scaling it up to feed 1,000 people for centuries and making sure the system never fails. Then there is food, and food is where the whole closed-loop concept gets really complicated. A human being needs about 2,000 to 2,500 calories per day to stay healthy. For a crew of 1,000, that is 2 to 2. 5 million calories per day, or roughly 700 to 900 million calories per year. You cannot carry that much food, not even freeze-dried, not even compressed into nutrient bars. The mass alone would sink the mission. The ship has to grow its own food, continuously, forever. And it has to grow enough that crop failures or pests or diseases do not cause famine. The good news is that plants are extraordinarily efficient at turning light, water, carbon dioxide, and a few minerals into edible calories. A square meter of well-managed hydroponic farmland can produce several kilograms of vegetables per month. Leafy greens like lettuce and spinach grow fast. Root vegetables like potatoes and carrots are calorie-dense. Legumes like beans and lentils provide protein. Grains like wheat and rice are staples that store well. Some studies suggest that about 50 to 100 square meters of farmland per person is enough to provide a balanced diet, depending on the crops and the efficiency of the system. For 1,000 people, that is 50,000 to 100,000 square meters, or 5 to 10 hectares. That is a lot of space, roughly 12 to 25 acres. Picture a farm that size crammed inside a rotating metal cylinder hurtling through space. Most generation ship designs assume multiple decks dedicated entirely to agriculture. Rows and rows of hydroponic troughs under bright LED grow lights, tended by crew members who spend their days planting seeds, monitoring nutrient levels, harvesting crops, and troubleshooting problems. The lights have to run continuously or on a timed cycle that mimics day and night, which means the ship's power system has to supply enormous amounts of electricity just to keep the plants alive. The lights also generate heat, which has to be removed by the ship's radiators, which adds to the thermal management problem. The plants themselves transpire water vapor, which has to be captured and recycled. The crops have to be rotated to avoid depleting the growing medium of nutrients. The nutrient solution has to be carefully balanced with nitrogen, phosphorus, potassium, calcium, magnesium, and trace elements. Too much of one nutrient and the plants get sick. Too little and they starve. Some crops fail. This is a fact of agriculture. Disease, pests, human error, equipment failure, lighting problems, nutrient imbalances, all of it leads to crop losses. On Earth, a farmer losing a field of wheat is an economic problem. On a generation ship, it is a survival problem. The ship needs redundancy in its food production. Multiple separate farms, ideally isolated from each other, so that a disease outbreak in one does not spread to the others. Stockpiles of dried or frozen food to cover gaps. Alternative protein sources that do not rely on plants. That is where insects come in. Crickets, mealworms, and black soldier fly larvae are extraordinarily efficient at converting organic waste into edible protein. They eat scraps, spoiled crops, food waste, even human feces if properly processed. They reproduce quickly, mature in weeks, and can be harvested in bulk. Per kilogram of feed, insects produce far more protein than cattle, pigs, or chickens, and they require far less space and water. A small insect farm, occupying a few cubic meters, can produce kilograms of protein per week. The insects can be dried, ground into powder, and mixed into other foods. They do not taste great on their own, but in a closed-loop system where every calorie counts, taste is a secondary concern. Some generation ship concepts include small livestock, chickens for eggs, rabbits for meat, fish in aquaponic systems where the fish waste fertilizes the plants, and the plants clean the water for the fish. Aquaponics is particularly elegant because it integrates two loops into one. The fish produce ammonia in their waste. Bacteria convert the ammonia into nitrates. The plants absorb the nitrates as fertilizer. The water, now cleaner, flows back to the fish tanks. Harvest some fish periodically and you have protein. Harvest the plants and you have vegetables. The system runs on light, fish feed, and a bit of maintenance. Some experiments on Earth have demonstrated aquaponic farms producing several kilograms of fish and dozens of kilograms of vegetables per square meter per year. Scale that up and you have a viable food source for a generation ship, assuming the system never crashes, and crashes are always possible. An aquaponic system is a living ecosystem, and ecosystems are fragile. If the bacteria die, the ammonia builds up and poisons the fish. If the fish die, the plants lose their nitrogen source and starve. If the water pump fails, everything dies within hours. The crew has to monitor the system constantly, test the water chemistry, adjust the pH, replace dead fish, clean the filters, and fix anything that breaks. This is not passive farming. This is active life support, 24 hours a day, every day, forever. Then there is waste, and not just food waste, human waste, broken equipment, worn-out clothing, packaging, dead plants, dead insects, dead fish. Everything that cannot be eaten or reused has to go somewhere. On Earth, you bury it, or burn it, or throw it in a landfill and forget about it. On a generation ship, you cannot forget anything. The ship is a closed system. Every atom that comes aboard at the start of the journey is all you have. Throw something away and it is gone. Lose enough atoms and eventually you run out of the materials you need to survive. So waste is not waste, it is raw material. Organic waste gets composted or digested by bacteria to break it down into simpler molecules. The carbon, nitrogen, phosphorus, and other elements get extracted and fed back into the hydroponic nutrient solution or the aquaponic tanks. The water gets recovered and purified. The solid residue gets dried, compressed and stored, or in some systems used as a growing medium for mushrooms or other decomposers that can extract the last traces of usable nutrients. Inorganic waste, plastics, metals, ceramics, get sorted and recycled. Metals get melted down and recast into new parts. Plastics get shredded and reformed. Anything that cannot be recycled gets stored in the least useful part of the ship, probably near the outer hull, where it can double as radiation shielding. None of this is theoretical. Closed-loop life support systems have been tested in small-scale experiments for decades. The Soviet BIOS-3 project in the 1970s sealed people inside a habitat with algae tanks and recycled air for up to 6 months. NASA's CLSLS program in the 1980s studied hydroponic farming and waste recycling. The European Space Agency's MELISA project has been running since 1989, developing a complete closed-loop system based on algae, bacteria, plants, and waste processing. China's Yukang-1 project, also called Lunar Palace, sealed 4 volunteers inside a 160 square meter habitat for 370 days in 2017 and 2018 with a life support system that recycled air, water, and food with minimal external inputs. All of these experiments worked, more or less. They proved that humans can survive in closed environments for months or even years. They also proved that closed-loop systems are incredibly demanding. The crew spent hours every day tending the plants, monitoring the air quality, fixing equipment, and cleaning filters. When something broke, they had to improvise repairs using only what was inside the habitat. When a crop failed, they had to ration food and hope the next harvest was better. The psychological strain of living in a sealed box with the same few people for months on end was by all accounts severe, and those were experiments lasting months, not centuries. A generation ship has to do all of that perfectly for hundreds of years. The crew has to maintain the farms, the recyclers, the filters, the pumps, the lights, the air scrubbers, the water purifiers, and everything else without let-up. They have to train the next generation to take over when they get old. They have to document every procedure so that knowledge is not lost. They have to plan for failures and have backups for the backups. Because if the loop breaks, if the oxygen stops flowing, or the water stops cycling, or the crops stop growing, the ship becomes a tomb. This is the hidden truth of a generation ship. The journey is not about propulsion or navigation, it is about ecology. The ship does not fly to another star. It drifts. The hard part is keeping the terrarium alive while it drifts. Every breath the crew takes is a breath that has to be recycled. Every sip of water is water that has passed through 100 bodies before. Every bite of food is built from atoms that have been cycled through plants, insects, fish, waste processes, and back into plants again. The entire mission rests on the assumption that human beings can engineer a closed ecosystem stable enough to survive centuries without outside inputs. We have never done that, not even close. The longest any closed system has ever supported human life is a year, maybe 2. A generation ship needs to do it for 500, and all of that assumes the systems themselves do not degrade. Filters clog, pipes corrode, pumps wear out, microbes evolve, pests adapt, diseases spread, nutrients get locked up in forms the plants cannot use, the pH drifts, the salinity drifts, trace elements accumulate or deplete. A closed-loop ecosystem is not a static thing. It is a dynamic, shifting, unstable equilibrium that has to be constantly nudged back into balance by people who understand what they are doing. If the knowledge is lost, if the crew forgets how to fix the algae tanks, or adjust the nutrient mix, or sterilize the water, the system fails, and once it fails, there is no recovery. The ship does not land, it does not turn around. It just keeps drifting through the dark, carrying the frozen corpses of a crew that could not keep the loop closed. That is the breath of life aboard a generation ship. Not romantic, not heroic, just relentless, grinding, careful maintenance of the chemical cycles that keep human bodies alive. It is a problem that has to be solved not once, but continuously, every single day, by people who will never see the destination and whose only reward is the knowledge that they kept the terrarium running for one more generation. And that next generation will have problems of its own. Problems that have nothing to do with water or air or food, and everything to do with the simple fact that human beings are not designed to live in metal tubes for their entire lives. That raising children in the void, teaching them to operate systems they did not build, and convincing them to care about a mission they did not choose, is a challenge that might be even harder than keeping the oxygen flowing. That comes next. That last generation of crew members, keeping the air cycling and the algae alive, has a problem that is not technical. The problem is that they are going to die, and before they die, they need to produce replacements, not robots, not clones, children. Human children who will be born inside the ship, grow up inside the ship, learn to operate systems they did not design, and eventually take over the work of keeping everyone alive. Then those children will have children of their own, and those children will have children, and this cycle has to continue without interruption for 10, maybe 20, maybe 30 generations, depending on how far the ship is going and how fast it can travel. And every single one of those generations has to stay healthy, stay fertile, and stay genetically viable, or the entire mission collapses before the ship ever reaches its destination. This is not a small problem. This is biology running headlong into mathematics, and the mathematics are brutal. A generation ship is a closed population. No one is immigrating. No one is bringing in fresh DNA from outside. Every person who will ever be born on that ship during the voyage is descended from the original crew who boarded at the start. And unless the ship is carrying frozen genetic material or has a very, very carefully managed reproductive program, That closed population is going to start running into serious genetic trouble within a few generations. Let's start with the basics. Genetic diversity is the variety of different genes within a population. The more diverse the gene pool, the healthier the population tends to be. Genetic diversity gives you resistance to disease, resilience to environmental stress, and a lower chance of inheriting 2 copies of harmful recessive genes. When a population is large and open, with individuals migrating in and out, genetic diversity stays high. When a population is small and closed, diversity drops fast. This is not speculation, it is observable fact. Island populations, isolated villages, endangered species with small breeding populations, all of them show the same pattern. As the gene pool shrinks, bad things start to happen. The first is inbreeding. When close relatives have children together, there is a much higher chance that harmful recessive genes will match up and express themselves. Most people carry a handful of recessive genes for genetic disorders. In a large population, those genes almost never find each other. In a small, closed population, they do. The result is higher rates of genetic disease, developmental disorders, reduced fertility, and shorter lifespans. The second problem is genetic drift. This is a random process where certain genes become more common and others disappear entirely, not because they are good or bad, but just because of chance. Flip a coin 100 times and you will get close to 50 heads and 50 tails. Flip it 10 times and you might get 7 heads and 3 tails. Small populations are like the 10 coin flips. Random variations get amplified, and useful genetic diversity can vanish by accident. So how many people do you need to avoid these problems? The question has been studied extensively because it applies to conservation biology, space colonization, and long-term survival scenarios. The answers vary depending on your assumptions, but there are some rough benchmarks. For short-term survival, a population of about 50 individuals can avoid immediate inbreeding problems for a few generations. For long-term viability over hundreds of years, most estimates suggest you need at least 150 to 500 people, and even then, you need to manage reproduction carefully. Some studies put the number higher, closer to 1,000 or even several thousand, if you want to maintain genetic health indefinitely without outside intervention. A generation ship traveling for 200 years, about 10 generations, sits right in the danger zone. Start with 150 people and you might be fine. Start with 100 and you are playing genetic roulette. Start with 50 and you are almost certainly doomed. One of the most frequently cited analyses suggests that a ship carrying about 160 people could maintain normal family structures and avoid inbreeding over a 200-year journey if, and this is a very big if, reproduction is carefully controlled. That means late childbearing, limited family sizes, and some form of social or institutional pressure to prevent close relatives from having children together. The same analysis notes that without those controls, the population would need to be significantly larger to avoid genetic collapse. For a 500-year journey, you would need more people. For a 1,000-year journey, significantly more. The longer the voyage, the more generations you go through, and the more opportunities there are for genetic drift and inbreeding to erode the health of the population. Now let's talk about what controlled reproduction actually means, because this is where the ethical problems start piling up. In a normal human society, people generally get to choose who they have children with. Love, attraction, compatibility, personal choice, these are considered fundamental rights in most cultures. On a generation ship, those rights run into direct conflict with the survival of the mission. If two people who are closely related fall in love and want to have children, their personal freedom threatens the genetic health of the entire population. If a large portion of the crew chooses not to have children at all, the population starts shrinking and the mission fails. If everyone has as many children as they want, the ship runs out of resources to support them. Every single one of these scenarios has happened in human history, and every one of them is a potential catastrophe in the closed environment of a generation ship. So some generation ship proposals include reproductive controls. These range from soft social pressures to hard institutional mandates. On the soft end, you have education programs that teach the crew about genetics and encourage them to make choices that benefit the population. You have cultural norms that discourage close relatives from pairing up and reward people who delay childbearing to optimize population size. You have matchmaking systems, voluntary or otherwise, that suggest compatible partners based on genetic diversity. On the hard end, you have mandatory genetic screening before reproduction is allowed. You have limits on the number of children per family. You have assigned partnerships where the ship's governing body decides who has children with whom based on genetic analysis and population models. You have reproductive lotteries where only certain individuals are allowed to reproduce in a given generation. And in the most extreme versions, you have mandatory sterilization of individuals carrying harmful genetic traits, or forced abortion of pregnancies that fail genetic screening. Every single one of these measures has been proposed in serious academic papers on generation ship design. And every single one of them is ethically horrifying when you think about it for more than 5 seconds. You are asking people, or more accurately forcing people, to surrender control over one of the most intimate and personal aspects of their lives for the good of a mission they did not choose to be part of. Remember, the only people who actually volunteer for a generation ship are the original crew. Everyone born afterward is conscripted at birth. They did not ask to be there. They did not agree to the mission. They are simply born into it. And now someone is telling them who they can love, who they can have children with, and how many children they are allowed to have. That is not a society. That is a breeding program. Some designs try to soften the blow by using stored genetic material instead of controlling the living population. The idea is simple. At the start of the mission, you collect sperm and eggs from a large number of donors, far more than the number of people actually on the ship. You freeze the samples and store them in cryogenic tanks. Then, when the time comes to have children, couples use assisted reproductive technology to conceive. The sperm and eggs come from the stored bank, ensuring high genetic diversity even though the living population is small. The children are still raised by the crew, but their genetic parents might be people who lived and died on Earth centuries earlier. This solves the inbreeding problem. It does not solve the psychological problem of raising children who are genetically unrelated to you, or the social problem of what happens when the stored genetic material runs out. A sperm or egg bank large enough to sustain a population for 500 years would need to contain thousands of samples, all carefully labeled, tracked, and maintained in working order. And cryogenic storage is not foolproof. Freezers fail. Power outages happen. Samples degrade over time. If the genetic bank is lost or contaminated, the mission is back to square one with a small closed population and all the genetic risks that entails. Another option is artificial wombs. If you can grow a human embryo outside a human body, you can decouple reproduction from the physical and emotional act of pregnancy. You can screen embryos for genetic health before they develop. You can control the population size precisely by choosing how many embryos to grow in a given year. You can even, in theory, carry frozen embryos from Earth and gestate them on the ship as needed, bypassing the need for a living population altogether. The ship becomes a transport for frozen potential humans rather than a habitat for living ones. Wake them up when you arrive, or grow them gradually during the journey to maintain a stable population. This idea shows up in science fiction constantly because it is elegant and solves multiple problems at once. It also requires technology we do not have. Artificial wombs are still in the experimental stage. Scientists have managed to grow animal embryos outside the body for limited periods, but a full gestation from conception to birth has never been achieved in humans. Even if the technology works, the ethical questions are staggering. Who decides which embryos get gestated and which stay frozen? Who raises the children when they are born? What happens if the gestating system fails halfway through a pregnancy? And perhaps most disturbingly, is it ethical to create human beings as a means to an end, as biological components of a mission they will never consent to? Let's assume, for the sake of argument, that you solve all of these problems. You have a population of 500 people. You have a genetic diversity plan. You have stored genetic material or controlled breeding or some combination of both. Everyone is cooperating. The population is stable. The children are being born at the right rate to replace the older generation as they die. Everything is going according to plan. You still have another problem: health. A generation ship is a closed system. Every pathogen, every bacteria, every virus, every fungus that comes aboard at the start of the mission is there for the duration, and pathogens evolve fast. A bacterial infection that was easily treatable with antibiotics in the first generation might evolve resistance by the third or fourth generation. A virus that caused mild illness in the original crew might mutate into something far more dangerous by the time it reaches their grandchildren. The ship has no way to import new medical supplies from Earth. No way to synthesize new antibiotics if the ones they have stop working. No way to develop a vaccine for a novel pathogen unless they have the lab equipment and trained personnel to do so on board. And the smaller the population, the faster diseases spread. On Earth, a disease outbreak can be contained by quarantine, by geographic distance, by the sheer size of the population. On a generation ship, everyone is living in close quarters, breathing the same recycled air, drinking the same recycled water, eating food grown in the same farms. An epidemic that infects one person can infect everyone within days. History is full of examples of small, isolated populations being devastated by disease: remote islands, Arctic research stations, ships on long ocean voyages. In every case, once a disease gets a foothold, it spreads rapidly and the population has nowhere to go. The ship cannot land, it cannot turn around, it cannot send the sick people home. Everyone is stuck. If the disease is lethal enough and spreads fast enough, it can kill a large portion of the crew before anyone figures out how to stop it. And if it kills the people who know how to operate critical systems, the ship itself fails. A medical crisis becomes an engineering crisis, becomes an extinction event. So the ship needs a hospital. Or more accurately, it needs a permanent medical staff with the training and equipment to handle everything from routine injuries to major surgery, to infectious disease outbreaks, to long-term chronic conditions. The medical staff needs to be large enough that losing a few members to illness or accident does not cripple the healthcare system. They need a full pharmacy with not just medicines, but the raw materials and equipment to synthesize new medicines when the stockpiles run low. They need diagnostic tools, imaging equipment, laboratory facilities for analyzing blood, tissue, pathogens, surgical suites, intensive care units, mental health services, And they need all of this to remain functional for centuries, maintained by people who may have been trained by someone who was trained by someone who learned from a textbook written on Earth generations ago. The knowledge problem is just as serious as the equipment problem. Medical knowledge degrades, techniques are forgotten. A surgeon who trained under a master surgeon can pass on most of what they learned to their apprentice. But the apprentice teaching the next generation will lose some details. The third generation loses more. The fourth generation is working from incomplete information. After 10 generations, critical knowledge might be gone entirely, and the crew is left with manuals they do not fully understand and equipment they cannot repair. This is not hypothetical. It has happened in human history over and over. Medical knowledge in Europe declined sharply after the fall of Rome and took centuries to recover. Traditional surgical techniques in some cultures were lost when master practitioners died without apprentices. A generation ship faces the same risk, only worse because there is no neighboring civilization to learn from. When the knowledge is gone, it is gone forever. And then there is the question of what happens to human biology itself over multiple generations in space. We do not know. Nobody does. The longest any human being has spent continuously in space is about 1.5 years, and that was aboard the International Space Station in low Earth orbit with regular resupply missions and the option to evacuate if something went seriously wrong. We know that microgravity causes bone density loss, muscle atrophy, fluid shifts that affect the eyes and brain, immune system suppression, changes in gut bacteria, cardiovascular deconditioning. Most of these effects are reversible if the person returns to Earth and goes through rehab. What we do not know is what happens if someone spends their entire life in microgravity or artificial gravity. Do they adapt? Do the changes compound over time? Do their children inherit any of those changes? A generation ship will almost certainly use rotation to create artificial gravity, but even that is not the same as real gravity. Artificial gravity, created by spinning a cylinder, produces a centrifugal force that pushes you toward the outer wall. To your body, it feels like gravity, but there are subtle differences. The Coriolis effect makes moving objects curve. Your inner ear, which relies on gravity to sense orientation, might behave differently in a rotating reference frame. The strength of the artificial gravity depends on how far you are from the axis of rotation. Stand near the center and you feel almost weightless. Walk toward the outer wall and the pull gets stronger. A child born and raised in that environment will develop in ways we cannot predict. Their bones might grow differently. Their muscles might adapt to the specific forces they experience. Their sense of balance might calibrate to a rotating world, and if the ship ever stops spinning, or if they land on a planet with real gravity, their bodies might not know how to cope. We also do not know how human reproduction works in space. No one has ever tried. Animals have been conceived and born in microgravity in a few experiments, and the results are mixed. Some species seem to handle it fine. Others show developmental abnormalities. Mammals, which rely on complex hormonal and circulatory systems during pregnancy, are particularly vulnerable. If artificial gravity is not perfect, if it is too weak or too uneven, pregnancy might become more difficult or dangerous. Birth defects might become more common. Infant mortality might rise, and because the population is small and closed, every failed pregnancy, every stillbirth, every child who does not survive to adulthood chips away at the genetic diversity and the population size. You cannot afford high infant mortality on a generation ship. There is no margin for error. Then there is the question of how fast generations turn over. A generation, in human terms, is usually defined as the average age at which people have children. On Earth, that has varied throughout history, from the late teens in some cultures to the 30s or 40s in others. Most generation ship models assume a generation time of about 25 years, which means a 250-year voyage would involve about 10 generations. But that number is not fixed. If people start having children earlier, the generation time shortens and you cycle through more generations in the same time period. If people delay childbearing, the generation time lengthens and you have fewer generations. Some proposals suggest deliberately extending the generation time to reduce the number of reproductive cycles and slow the rate of genetic drift. Have children later in life, keep the population older and more experienced, and minimize the turnover. The trade-off is that older parents have higher risks of genetic abnormalities in their offspring, and a population of mostly middle-aged and elderly people has fewer working-age adults to maintain the ship and do the physical labor of farming and repair work. There is no good answer. Every choice is a trade-off. A young population reproduces faster and has more energy, but they have less experience and are more likely to make mistakes. An older population has more knowledge and stability, but they are more fragile and less able to handle physical demands. A large population provides genetic diversity and redundancy, but it strains the ship's resources. A small population is easier to sustain, but it is vulnerable to disease, accidents, and genetic collapse. The optimal population size and structure depends on the length of the journey, the size of the ship, the efficiency of the life support systems, and a dozen other variables that cannot be known for certain until the ship is built and the mission is underway. And all of this assumes the population cooperates, that people follow the reproductive guidelines, that they accept restrictions on their personal freedom for the good of the mission, that they have children when the plan says they should, with the partners the plan says they should pair with, and raise those children to do the same. In other words, it assumes the generation ship functions less like a human society and more like a machine where every component does exactly what it is supposed to do without complaint or deviation. Human beings do not work that way. They fall in love with the wrong people. They rebel against authority. They make choices based on emotion rather than logic. They forget why the rules exist and decide the rules are stupid. And on a generation ship, where every single person born after the launch is living a life they never chose, the odds of rebellion, resentment, and social breakdown are high, very high. This brings up a question that is rarely discussed in the technical literature, but is absolutely central to the concept. What happens if a generation decides they do not want to have children, not as individuals, but as a collective choice? Maybe they look around at the metal walls they have lived inside their entire lives and decide they do not want to bring new life into this prison. Maybe they resent their parents for having them. Maybe they see no point in perpetuating a mission that will not benefit them personally. Or maybe they are simply tired, depressed, and hopeless. If an entire generation refuses to reproduce, the mission ends. The ship keeps flying, but there is no one to replace the crew when they die. The last generation grows old. The systems start failing because there is no one left who knows how to fix them, and eventually the ship becomes a tomb full of elderly people waiting for the oxygen to run out. That is not a technical failure. That is a social failure, and it is just as deadly. You can engineer a perfect life support system. You can design a genetically optimal breeding program. You can plan for every biological contingency. But if the people on board stop caring, stop cooperating, stop believing in the mission, none of it matters. The ship fails not because the oxygen recyclers broke or the crops died, but because the generations in the dark looked at the life they inherited and said no. Which brings us to the real problem with generation ships. Not the biology, not the genetics, not the medicine. Those are hard, yes, but they are at least solvable with enough planning and resources. The real problem is the minds of the people inside. Human psychology, human society. The weight of living your entire life in a metal tube with no escape, knowing you will die before the journey ends, raising children who will also die before the journey ends, asking them to raise their own children to continue a mission that none of them ever asked to be part of. That weight, that crushing psychological burden, is what comes next. And it might be the thing that breaks the ship long before it ever reaches another star. The ship is spinning, the air is cycling, the farms are producing food, the population is stable, the children are being born, the genetic diversity plan is holding, everything on paper is working, the generation ship has cleared every technical hurdle, the engineering is sound, the biology is under control, the systems are humming along. And yet, despite all of that, despite solving every mechanical and biological problem, the mission is still doomed. Not because the hull will crack, or the oxygen will run out, or the crops will fail. Because the people inside, the human beings who are supposed to keep this whole improbable enterprise running for centuries, are going to break. Maybe not in the first generation, probably not in the second. But somewhere down the line, after enough decades of confinement, after enough generations born into a world they never chose, after enough time staring at the same metal walls and breathing the same recycled air and knowing with absolute certainty that they will live and die without ever setting foot on a planet, something inside the social structure is going to snap. And when it does, the ship becomes a flying tomb. This is the part that does not show up in the engineering diagrams. You cannot model it with equations or test it in a lab or solve it by adding more redundancy. The weight of the void is not a technical problem, it is a human one. And human problems, unlike mechanical ones, do not come with instruction manuals or replacement parts. Let's start with the environment, because the environment is where the psychological damage begins. A generation ship is, by necessity, small. Not small in the sense of a cramped apartment or a crowded subway car. Small in the sense that it is a fixed, enclosed space that never changes. On Earth, even if you live in the same house your entire life, the world outside is vast. You can walk down different streets. You can visit new cities. You can stand on a beach or hike through a forest or sit in a park and watch clouds drift by. The scenery changes, the seasons change, the people change. There is variety, there is novelty. Your brain, which evolved to process an ever-shifting environment full of threats and opportunities, gets the stimulation it needs to stay healthy. On a generation ship, there is no outside. There are no new streets. There are no forests or beaches or parks. There is the ship, the same corridors you walked yesterday, the same living quarters, the same dining hall, the same observation windows looking out at the same unchanging blackness. Maybe, if you are lucky, you can see stars, but even those do not move in any noticeable way over the course of a human lifetime. The ship is in interstellar space, so far from any sun that the stars are just faint pinpricks of light that do not shift or twinkle or give any sense of motion. The view outside is static. The view inside is static. Everything is static. Psychologists have a term for what happens to people in environments like this: sensory deprivation, or more accurately, stimulus deprivation. Your brain needs input. New sights, new sounds, new experiences. Without that input, it starts to malfunction. Studies of people in isolation, prisoners in solitary confinement, researchers spending months in Antarctic stations, sailors on long voyages, all of them report the same symptoms: depression, anxiety, irritability, difficulty concentrating, memory problems, hallucinations, a creeping sense of unreality. Some people adapt better than others, but nobody comes out of prolonged isolation unscathed. And a generation ship is not isolation for months or even years. It is isolation for lifetimes, for generations. The original crew, the people who volunteered to board the ship, at least have memories of Earth. They remember what it feels like to stand outside under an open sky. They remember rain, wind, the smell of soil after a storm, the sound of birds, the feeling of sunlight that is not filtered through a viewport or simulated by a grow light. Those memories might fade over time, might become idealized and distorted, but they are there. They provide a psychological anchor, a sense that the ship, as confining as it is not the entire universe, that there is something beyond the walls worth reaching. Their children do not have that anchor. The second generation is born on the ship. They grow up in the same metal corridors. They learn about Earth from stories and videos and textbooks, but they have never experienced it. To them, Earth is not a memory. It is an abstraction, a fairy tale. A place that might as well be imaginary because it is unreachable and unknowable in any direct sense. The ship, on the other hand, is real. The ship is everything. The walls, the floors, the ceilings, the hum of the ventilation system, the taste of hydroponic vegetables, the faces of the same few hundred or few thousand people they see every day. That is their world. That is all they know. Now imagine being the third generation, or the fifth, or the 10th. You are born into a world where no one alive has ever seen Earth. The stories about oceans and mountains and forests are handed down like myths. The mission, the reason the ship exists, the destination it is traveling toward, all of that is abstract too. You are told that your ancestors left Earth to reach another star, to find a new world, to give humanity a future among the stars. But you did not leave Earth. You did not choose this mission. You were born into it. Your parents were born into it. Your grandparents were born into it. The ship is not a vehicle taking you somewhere. It is a prison you will never escape. And the worst part is that the bars are not physical, they are temporal. You cannot leave because the journey will not end in your lifetime. You are serving a sentence imposed by people who died before you were born for a crime you did not commit. That psychological burden is staggering, and it does not just affect individuals, it affects the entire social structure, because a generation ship is not just a machine, it is a society. And societies need governance, they need rules, they need leadership. They need institutions that maintain order and resolve disputes and make decisions about resource allocation and labor and all the things that keep a community functioning. On Earth, governments rise and fall, leaders are elected or overthrown, institutions evolve, cultures change, there is churn, there is dynamism. On a generation ship, the government cannot fall because there is nowhere else to go. The institution cannot be overthrown because there is no outside power to replace it. The society is trapped in a box with itself, and if the social order breaks down, everyone dies. So how do you maintain governance over centuries? How do you ensure that the leadership structures put in place by the original crew remain legitimate and effective 10 generations later? This is not a hypothetical question. It is a problem that has destroyed civilizations throughout human history. Dynasties collapse, empires fragment, revolutions overthrow old orders, and in every case, the breakdown happens because the system loses legitimacy in the eyes of the people it governs. Either the rulers become corrupt or incompetent, or the people stop believing that the rulers have the right to rule, or external pressures destabilize the society faster than it can adapt. A generation ship does not have external pressures, it has internal ones. And those internal pressures, the resentment, the boredom, the sense of futility, build over time like water behind a dam. Some generation ship designs propose a democratic system where the crew votes on leaders and policies. Democracy works well in societies where people have shared interests and a sense of collective identity. It works less well when the population is divided, when different groups have conflicting goals, when there is no common enemy to unite against. On a generation ship, the population is divided by generation. The older generation remembers why the mission matters. The younger generation does not. The older generation has experience operating the ship's systems. The younger generation resents being told what to do by people who will not live to see the destination. Elections in that environment do not produce consensus. They produce factionalism, and factionalism in a closed system is lethal. Other designs propose a more authoritarian structure. A captain or a council with absolute authority, appointed for life or passed down through a lineage. The logic is that strong centralized control prevents the kind of fracturing that kills democracies. The problem with authoritarianism is that it works only as long as the people being ruled accept the authority of the rulers. And over generations, that acceptance erodes. Why should the 10th generation obey orders from a captain whose authority derives from a mission plan written by people who died 200 years ago? What happens when the captain makes a decision that a significant portion of the crew disagrees with? On Earth, dissidents can leave, they can emigrate, they can start a new society somewhere else. On a generation ship, there is no somewhere else. Dissent cannot be released. It builds, and eventually it explodes. History is full of examples. Mutinies on long ocean voyages where the crew turned on the captain. Rebellions in isolated colonies where the settlers overthrew the appointed governor. Coups in closed societies where the military took power from a failing civilian government. In every case, the common thread is the same. A population trapped in a situation they cannot escape, under leaders they no longer trust, with no release valve for their frustration. A generation ship is all of those scenarios combined and stretched across centuries. Now add in cultural drift. Culture is not static, it evolves. Languages change, beliefs shift, traditions are reinterpreted or forgotten. On Earth, that process is driven by contact with other cultures, by technological change, by generational turnover, by migration and trade and conquest. On a generation ship, there is no contact with other cultures. The only outside influence is the mission itself, the goal of reaching another star, and even that influence weakens over time as the destination remains impossibly distant and the people alive have no personal connection to the decision to leave Earth. What you end up with is a culture that drifts inward, that becomes more insular, more focused on the internal dynamics of the ship, and as it drifts, it fragments. Imagine the original crew, the volunteers who boarded the ship, had a shared culture. Maybe they were all from the same country, or spoke the same language, or shared the same values. That shared culture held them together. It gave them a common identity. It made cooperation easier. Their children inherit that culture, but they interpret it through the lens of their own experiences. They did not choose to leave Earth. They were born on the ship. The stories their parents tell about Earth start to sound like propaganda. The mission starts to sound like a lie. Maybe some of them embrace the mission anyway, out of loyalty or faith or a sense of duty. Maybe others reject it. And now you have two subcultures forming, the believers and the skeptics. the loyalists and the rebels. Each generation, the divide widens, new subcultures form, new languages or dialects emerge, new beliefs take root. After 10 generations, the crew might not even recognize the culture of their ancestors. The ship, which was supposed to carry humanity to the stars, might instead carry a fragmented, divided, barely functional society that has no idea why it is even traveling. And then there is the generation gap. On Earth, the gap between parents and children is a constant source of tension. The younger generation thinks the older generation is out of touch. The older generation thinks the younger generation is reckless and disrespectful. That gap is manageable because it is temporary. The younger generation eventually grows up, has children of their own, and becomes the older generation. The cycle continues. On a generation ship, the gap is amplified beyond recognition, because the divide is not just between parents and children. It is between the generation that remembers Earth and the generation that does not. Between the generation that believes in the mission and the generation that sees it as a prison sentence. Between the generation that built the ship and the generation that inherited it. This is not a small problem. This is a civilizational fault line, and it runs through every aspect of life on the ship. The older generation controls the knowledge. They know how to operate the systems. They know how to repair the equipment. They know the procedures that keep everyone alive. The younger generation resents that control. They see the older generation as gatekeepers hoarding power. They see the mission as a trap designed by dead people to keep them enslaved. And the older generation sees the younger generation as ungrateful, as spoiled, as a threat to the mission. Both sides are right, both sides are also wrong. And there is no way to resolve the conflict because both sides are trapped together with no escape. Now let's talk about what happens when people lose purpose. Because purpose is what keeps societies functional. People need to believe that their lives matter, that their work means something, that their sacrifices will lead to something better. On a generation ship, that belief is hard to sustain. The original crew had purpose. They chose to board the ship. They chose to leave Earth. They accepted that they would die before reaching the destination because they believed the mission was worth it. They were pioneers, explorers, visionaries. Their purpose was clear. The second generation has a harder time. They did not choose the mission, but at least their parents did. The stories are fresh. The connection to Earth is one generation removed. The purpose, even if it is inherited, is still tangible. They can look at their parents and see people who believed, who sacrificed, who made the journey possible. That gives them something to hold on to, a reason to keep going. By the fifth generation, the connection is gone. Earth is ancient history. The original crew are names in a textbook. The mission is just a fact of life, like gravity or the recycled air. There is no personal connection, no emotional investment. The destination, Proxima Centauri, or wherever the ship is headed, is still centuries away. No one alive will ever see it. No one alive has ever known anyone who knew anyone who saw Earth. The ship is not taking them somewhere. It is just where they live and where they will die. The purpose that motivated the original crew has evaporated. What is left is routine, obligation, the grinding day-to-day work of maintaining a ship that will keep flying long after they are dead. And humans are not good at sustaining effort without purpose. We need meaning, we need goals, we need to believe that what we do matters. When that belief disappears, societies collapse. People stop working, they stop caring, they stop cooperating. On Earth, when a society loses purpose, people can leave. They can find new communities, new identities, new reasons to live. On a generation ship, there is no leaving. There is only the ship, And if the ship loses its collective sense of purpose, the mission fails not because the systems broke, but because the people stopped trying. Some proposals suggest using education to combat this. Teach every generation about the mission. Drill into them the importance of reaching the destination. Make the mission sacred. Turn it into a religion that works sometimes. Religion has sustained communities through impossible hardships for millennia. It gives people a reason to endure suffering, a promise that their sacrifice will be rewarded, if not in this life, then in the next, or in this case, in the lives of their distant descendants. But religion is a double-edged sword. It can unify. It can also divide. What happens when a faction decides the mission is not sacred? When they reject the teachings of the older generation and start worshipping something else? What happens when the religion fractures into sects, each one claiming to have the true interpretation of the mission? Religious wars have destroyed civilizations on Earth. On a generation ship, a religious war would destroy everyone. Other proposals suggest using entertainment and virtual reality to combat the psychological strain. Give the crew access to simulations of Earth. Let them walk through virtual forests, or swim in virtual oceans, or climb virtual mountains. Give them the illusion of variety and novelty. That might work for a while. Virtual reality is already good enough to trick the brain in short bursts, but long-term, the brain adapts. It learns that the forest is not real, that the ocean is not real, that the experience, no matter how vivid, is a lie. And once the brain knows it is being tricked, the illusion loses its power. The crew might spend hours in virtual reality, but when they take off the headset, they are still in the same metal corridors, still trapped, still hopeless. The virtual world becomes a crutch, then an addiction, then a prison of its own. And then there is the most disturbing possibility, that a generation, or a significant portion of one, simply gives up, not violently, not dramatically, just quietly. They stop having children, they stop maintaining the systems, they stop participating in the life of the ship. They go through the motions until the motions stop making sense, and then they just wait to die. This is not hypothetical. It has happened in human societies facing prolonged stress and hopelessness. Birth rates plummet, suicide rates climb, communities dissolve. On Earth, outside intervention can sometimes reverse the decline. Aid organizations, neighboring countries, new opportunities. On a generation ship, there is no intervention, there is no aid, there is no escape. If a generation collectively decides the mission is not worth continuing, the mission ends. The ship keeps flying, but the people inside stop being a society and become a collection of individuals waiting for the oxygen to run out. Now imagine you are the leadership trying to prevent all of this, trying to maintain order, trying to keep people motivated, trying to prevent rebellion or apathy or cultural collapse. You cannot threaten them with exile because there is nowhere to exile them to. You cannot offer them rewards beyond what the ship already provides. You cannot promise them freedom because freedom does not exist. The only tools you have are social pressure, propaganda, and force, and all three of those tools erode over time. Social pressure works when the community is cohesive, when people care what their neighbors think, when reputation matters. On a generation ship, after enough generations, the community is not cohesive, it is fractured. Social pressure only works within each faction, and the factions themselves might be in conflict. Propaganda works when people trust the source, when the message aligns with their lived experience. On a generation ship, after enough generations, the propaganda rings hollow. The promises of a better future on a distant world sound like lies because no one alive has ever seen that world or met anyone who has. Force works when the leadership has a monopoly on violence, when there is a clear hierarchy, when the ruled accept the legitimacy of the rulers. On a generation ship, after enough generations, that legitimacy is gone. The crew might obey out of habit or fear, but the moment the fear weakens, the moment someone charismatic enough stands up and says no, the hierarchy collapses. And when the hierarchy collapses, when the social order breaks down, the ship does not explode, it does not depressurize, it does not crash, it just stops functioning. Systems that require maintenance go unattended. Repairs that need to be made are ignored. Conflicts that used to be resolved peacefully escalate into violence. The farms are neglected. The water recyclers are neglected. The air scrubbers are neglected. And slowly, over months or years, the life support systems fail. The air gets harder to breathe. The water gets scarcer. The food runs out. And the people who are left, the survivors of the social collapse, realize too late that they cannot put the pieces back together because the knowledge is gone and the tools are broken and there is no one left who remembers how anything worked. That is the weight of the void. Not the physical isolation, though that is crushing enough. The psychological and social isolation. The knowledge that you are trapped in a metal tube with the same people, the same walls, the same unchanging environment for your entire life, that your children will be trapped, that their children will be trapped, that the destination is so far away it might as well be imaginary, that the mission you are serving was designed by people who are dust, for reasons that no longer make sense, and that even if you succeed, you will never know it because you will be dead centuries before the ship arrives. Human beings were not designed to carry that weight. We are not built for multi-generational confinement. We are not built to sustain purpose across centuries without feedback or reward. We are not built to live in a society that never changes, never grows, never offers escape. And yet a generation ship demands exactly that. It demands that people do the impossible. That they stay sane, stay cooperative, stay motivated, for lifetimes, for generations, with no guarantee that any of it will matter. Some scientists argue that the weight is bearable, that humans are adaptable, that with the right education, the right social structures, the right cultural programming, a generation ship could work. Maybe they are right. Maybe a carefully designed society with just the right mix of governance and purpose and distraction could hold together for centuries. Or maybe the weight of the void is simply too much. Maybe asking people to live their entire lives as cogs in a machine designed by dead strangers is asking the impossible. Maybe the ship will fail not because the engineering is flawed, but because the people inside were never meant to live that way. And if the ship does fail, if the society collapses, or the crew loses hope, or a rebellion tears the mission apart, the only thing left is the question of what could have been done differently, what knowledge could have been preserved, what lessons could have been taught, what systems could have been designed to keep the next generation connected to the mission, connected to the purpose, connected to the idea that the journey, as brutal and hopeless as it feels, is still worth completing. That brings us to the next challenge, not keeping people alive. Not keeping them sane, but keeping them educated. Teaching them the skills and the knowledge and the history they need to operate the ship. To maintain the systems, to understand why they are traveling. And more than that, to pass that knowledge forward, intact, across generations that have no personal connection to where they came from or where they are going. Because if the knowledge is lost, the mission is lost. And keeping knowledge alive across centuries in a closed society with no outside input might be the hardest problem of all. The ship does not fall apart because the hull cracks or the reactor fails. It falls apart because someone in the seventh generation does not know how to fix the air scrubber, and the person who could have taught them died before passing on the knowledge. The ship becomes a tomb not because of an engineering failure, but because of an educational one. Because somewhere along the line, the chain of knowledge broke, and no one left alive knows how to splice it back together. This is the hidden crisis of a generation ship, not the life support, not the genetics, not even the crushing weight of confinement. The real crisis is education. Teaching the children, teaching their children, teaching generation after generation for centuries without access to universities or libraries or experts from Earth, without textbooks that can be reprinted when they wear out, without the internet or video lectures or any of the infrastructure that makes education on Earth possible. A generation ship is a sealed box, and everything inside that box when the journey begins is all the crew will ever have. Every book, every manual, every lesson plan, every piece of knowledge. If it is not on the ship at launch, it does not exist. And if it is on the ship but gets lost or forgotten or misunderstood somewhere along the way, it might as well have never existed at all. Let's start with what needs to be taught, because the list is longer than most people realize. The obvious stuff first. Engineering. The crew needs to know how to operate and maintain every system on the ship. The reactors, the life support, the water recyclers, the farms, the computers, the airlocks, the structural integrity monitoring systems, the navigation systems, the propulsion, if the ship has active propulsion rather than just coasting. Every single one of these systems is critical. If the oxygen recycler breaks and no one knows how to fix it, everyone dies. If the water purification system fails and no one understands the chemistry behind it, everyone dies. If the reactor shuts down and no one can restart it, the ship goes dark and cold and everyone dies. Engineering is not optional, it is survival. But engineering is not enough. The crew also needs to understand the underlying science, physics, chemistry, biology, mathematics. Because a manual can tell you how to replace a part, but it cannot tell you what to do when the part you need does not exist, and you have to fabricate a replacement from materials you have on hand. For that, you need to understand why the part works, what forces it has to withstand, what materials will hold up under those conditions, how to test your improvised replacement before you install it and hope it does not fail. Science is not just academic, it is the foundation that lets you solve problems the manual writers never anticipated. Then there is medicine. The ship needs doctors, surgeons, nurses, pharmacists, diagnosticians, people who can treat injuries, illnesses, infections, chronic conditions, people who can deliver babies, people who can perform emergency surgery when someone gets hurt in an accident, people who can recognize the early signs of an epidemic and stop it before it kills half the crew. Medical knowledge is vast. A single human body is extraordinarily complicated, and keeping it alive requires understanding anatomy, physiology, pathology, pharmacology, and a dozen other fields. A general practitioner on Earth trains for years and still only knows a fraction of what there is to know. A generation ship cannot afford specialists because there are not enough people. The medical staff has to be generalists who can handle everything from a broken bone to a heart attack to a difficult birth, and they have to train the next generation to do the same. Now add agriculture, because the farms are not automatic. Hydroponics and aquaponics and algae tanks all require constant monitoring and adjustment. The crew needs to understand plant biology, nutrient cycles, pest management, disease control, how to diagnose why a crop is failing and how to fix it. how to breed plants for better yields or resistance to disease, how to maintain the delicate balance of an aquaponic system where the fish and the plants and the bacteria all depend on each other. If the agricultural knowledge is lost, the farms fail. If the farms fail, the crew starves. Education in agriculture is education in survival. And then there is the knowledge that is not directly about keeping the ship running, but is still critical. History, why the mission exists, where the crew came from, what Earth was like, why humanity decided to build generation ships and send them to the stars. If the younger generations do not know this, if they grow up thinking the ship is just the way things are with no context or explanation, the mission loses meaning. They have no reason to care, no reason to keep going, no reason to maintain the systems or raise their children or do any of the grinding, thankless work that keeps everyone alive. Purpose has to be taught. History is how you teach it, philosophy and ethics. A generation ship is a closed society with no outside authority. The crew has to govern itself. They have to resolve disputes. They have to make decisions about resource allocation, reproduction, punishment for crimes, and 1,000 other issues that come up when people live together. They need a framework for thinking about right and wrong, fairness and justice, individual rights versus the collective good. On Earth, societies develop these frameworks over centuries, influenced by religion, law, tradition, and philosophy. A generation ship does not have centuries. It has to carry a working ethical framework from the start and teach it to every generation. If the framework is lost or rejected, the society fractures and the mission fails. Art and literature, music, culture. These might sound like luxuries, but they are not. They are what make life bearable. What give people something to care about beyond the machinery and the checklists and the endless maintenance. A generation ship is not just a vehicle, it is a home, and homes need beauty. They need stories, they need songs. They need the accumulated creative output of humanity to remind the crew that they are not just biological components in a machine, they are people, inheritors of thousands of years of human culture. If that culture is lost, if the ship becomes a sterile place where nothing matters except function and efficiency, the crew loses their humanity. And humans who lose their humanity stop cooperating, stop caring, stop trying. So the curriculum for a generation ship is massive. Engineering, science, medicine, agriculture, history, philosophy, ethics, art, literature, music, all of it has to be taught. All of it has to be preserved, and it all has to fit into the limited time and resources available to a small population living in a closed environment where most people have day jobs keeping the ship running. On Earth, education is a multi-decade process supported by massive institutions. Schools, universities, libraries, museums, research labs, publishing houses, governments fund education. Corporations fund research. Knowledge is distributed across millions of people and trillions of pages of text and petabytes of data stored in servers around the world. If a single school closes or a library burns down, the knowledge is not lost because it exists in 100 other places. A generation ship does not have that redundancy. It has a few thousand people at most, a single library, a single set of servers, and no way to call Earth for backup if something goes wrong. Everything has to work the first time, every time, for centuries. Let's talk about the practical side first. Teaching the engineering and technical skills that keep the ship running. The easiest approach is apprenticeship. Pair an experienced engineer with a younger crew member and have them work together for years until the younger person has learnt the systems inside and out. This works. It is how most technical knowledge was transmitted for most of human history before formal schools existed. The problem is that apprenticeship is slow and it relies on personal relationships. If the master engineer dies before the apprentice is fully trained, knowledge is lost. If the apprentice is not particularly talented or motivated, knowledge is degraded. After enough generations, the quality of the training declines. The 8th generation engineer knows less than the 7th, who knew less than the 6th, and so on until someone tries to repair a critical system and has no idea what they are doing. So you need formal education, classrooms, teachers, textbooks, a structured curriculum that ensures every generation learns the same core material, that works better than apprenticeship alone, but it has its own problems. Teachers need training, textbooks need to be written, printed and maintained. Physical books wear out, paper degrades, ink fades. After a few generations of use, the textbooks are illegible and you need new copies. That means you need a printing press or a digital equivalent, and you need people who know how to operate it, and you need raw materials, paper or electronic components, or whatever medium you are using to store information. If the printing system fails or the electronic storage degrades, the textbooks are gone and the knowledge goes with them. Digital storage seems like the obvious solution. Store everything on hard drives or solid-state drives or some other medium. Back it up redundantly. As long as the computers keep running, the knowledge is safe. Except digital storage is not forever. Hard drives fail, flash memory degrades, magnetic tape deteriorates, optical discs scratch and delaminate. The lifespan of most digital storage media is measured in decades, not centuries. A generation ship traveling for 500 years would need to migrate its data to fresh storage media multiple times during the journey. That requires working computers, working fabrication equipment to produce new drives, and people who understand data storage well enough to perform the migration without losing anything. If any step in that chain breaks, the data is gone. Some proposals suggest engraving critical information onto metal plates or ceramic tablets, materials that will not degrade over centuries. Engrave the engineering manuals, the repair procedures, the scientific principles, everything essential, onto durable physical media and store it in a vault. That works as a last resort backup, but it has limitations. Engraved text cannot be searched the way digital data can. You cannot update it when new information is discovered or old procedures are refined, and engraving is space-intensive. A single engineering manual might fill hundreds of pages. Engrave all the manuals for every system on the ship, and you are looking at tons of metal or ceramic, which adds mass and takes up space that could be used for something else. The best solution is probably a layered approach. Digital storage for everyday use, physical books as a medium-term backup, engraved tablets as a last resort, redundancy at every level, and a dedicated crew whose only job is to maintain the library, to check the digital storage for errors, to print new copies of books when the old ones wear out, to verify that the engraved tablets are still legible, to catalog and organize the information so it can be found when it is needed. Librarians, essentially, not a luxury, a necessity. Now let's talk about what happens when the knowledge starts to degrade despite your best efforts. Because it will. Degradation is inevitable in a closed system over long time scales. Start with language. The original crew speaks, let's say, English. Their children grow up speaking English too. But language evolves. New words are coined. Old words change meaning. Slang develops. After a few generations, the English spoken on the ship might diverge from the English spoken on Earth. After 10 generations, it might be a distinct dialect. After 20, it might be almost unrecognizable. That matters because the engineering manuals, the textbooks, the historical records, all of them are written in the English of the first generation. If the later generations cannot read that English fluently, they cannot fully understand the manuals. They might get the gist, but they will miss details, misinterpret instructions, make mistakes, and in a closed environment where mistakes can be fatal, linguistic drift is a serious problem. Some designs propose freezing the language, teaching a formal standardized version of the language alongside the everyday spoken dialect. Make the formal language sacred, the language of the manuals and the textbooks and the official records. Drill it into every child so they can read the old texts, even if they do not speak that way in daily life. That works, maybe. It is essentially what Latin was for medieval Europe. A frozen language that scholars used to read ancient texts, even though no one spoke it at home anymore. But Latin eventually died as a living language, and the knowledge encoded in Latin texts became inaccessible to anyone who had not spent years studying it. A generation ship cannot afford to have its technical manuals become the equivalent of medieval manuscripts that only a tiny educated elite can read. Then there is the problem of context. A manual written by the original engineers assumes a certain level of background knowledge. It assumes the reader understands the basic principles of physics and chemistry and engineering. It assumes the reader has seen examples of similar systems on Earth or in training simulations. It assumes the reader can fill in gaps and make intuitive leaps based on experience. But after a few generations, that background knowledge erodes. The later generations have never been to Earth. They have never seen examples of anything except what is on the ship. The intuitive leaps that the manual assumes are no longer intuitive. The gaps cannot be filled. The manual stops being a teaching tool and becomes a cryptic set of instructions that sort of work if you follow them exactly but do not explain why. This is not hypothetical. It happens on Earth all the time. Ancient technologies are lost because the people who understood them died without writing down the full details. Roman concrete, which was incredibly durable, was a lost technology for centuries because no one wrote down the exact recipe or the reasoning behind it. Damascus steel, famous for its strength and sharpness, is still not fully understood because the techniques were passed down orally and died with the last smiths who knew them. Greek fire, a weapon used by the Byzantine Empire, is a mystery because the formula was a closely guarded secret that was never written down. A generation ship cannot afford to lose technologies this way, but preventing it requires more than just writing things down. It requires writing them down in a way that someone with no background, no context, no prior experience can understand and replicate centuries later. That is extraordinarily difficult. One solution is to build education around the Socratic method. Do not just teach people what to do. Teach them how to think, how to ask questions, how to test hypotheses, how to troubleshoot, how to derive first principles from observation. If the later generations understand the underlying logic of the systems, they can reconstruct lost knowledge even if the manuals are incomplete or damaged. This works in theory. In practice, teaching critical thinking is much harder than teaching rote procedures. It requires skilled teachers who understand the material deeply enough to guide students through the reasoning process. And it requires students who are curious and motivated, which is not guaranteed. A child born on a generation ship did not choose to be there. They might resent the mission. They might not care about learning how the reactor works. Forcing them to learn anyway is possible, but forced learning rarely produces the kind of deep understanding needed to troubleshoot novel problems. So you end up with a filtering problem. You need to identify the children who are capable and motivated enough to become the next generation of engineers and scientists and doctors, and you need to give them intensive training. The rest of the crew can learn basic skills, but the deep knowledge has to be concentrated in a smaller group. That smaller group becomes the intellectual elite of the ship. They hold the keys to survival. Everyone else depends on them, and that creates a power dynamic that can destabilize the society. The elite might become arrogant, the rest of the crew might resent them, factions might form. And if the elite fails to pass on the knowledge, either because they die unexpectedly or because they deliberately hoard it to maintain power, the mission is doomed. Now let's talk about teaching purpose. Because all the technical knowledge in the world is useless if the crew does not care about the mission. Purpose is what keeps people motivated, what makes them willing to do the hard work of maintaining the ship, even though they will never benefit personally. The original crew had purpose. They chose the mission. They believed in it. Their children inherit some of that belief, but it is second-hand. By the third generation, it is third-hand. By the 10th, it is a story told by people who are telling a story they were told. The emotional connection weakens. The mission starts to feel abstract. And abstract missions do not motivate people to scrub algae tanks or repair broken pumps or spend years learning complicated technical skills. So how do you keep the mission alive? One approach is to make it religious. Turn the journey into a sacred pilgrimage. The ship is not just a vehicle, it is an ark carrying the chosen people to a promised land. The destination is not just a planet, it is salvation. The mission is not just a goal, it is a divine command. Religion is powerful. It can sustain communities through incredible hardships. It can give meaning to suffering. It can make people willing to sacrifice their own happiness for a future they will never see. The downside is that religion can also fracture and divide. Heresies emerge, sects split off, fanatics take extreme actions. And if the religion becomes more important than the mission itself, the crew might start making decisions based on doctrine rather than practicality. They might refuse to repair a system because it conflicts with their beliefs. They might interpret a malfunction as divine punishment. They might turn against the original mission and decide the ship should return to Earth or stop traveling or self-destruct as a form of martyrdom. Another approach is to make the mission educational in itself. Teach history not as dry facts, but as a story, the story of humanity. The story of Earth, the story of exploration and discovery, and the drive to reach beyond what is known. Show the children that they are part of something larger than themselves, that they are the inheritors of thousands of years of human striving, that the ship is not a prison, but a continuation of the same journey that led humans out of Africa, across oceans, to every corner of the Earth, and finally into space. That story can be compelling. It can give people pride, a sense of identity, a connection to the past and the future. The challenge is keeping the story alive and relevant across generations. History taught badly is boring. History taught well is inspiring. And inspiring history requires skilled teachers who can make the past feel immediate and real. Some generation ship designs propose using cultural artifacts to preserve the connection to Earth. Carry works of art, sculptures, paintings, recordings of music, films, photographs. Let the crew see and hear and experience the culture they came from. Build a museum on the ship where people can walk through and see what Earth was like. That works as long as the artifacts are maintained. But art degrades, paint fades, film deteriorates, digital recordings corrupt. After a few generations, the artifacts might be damaged or lost, and even if they survive, they are still just objects. They do not explain themselves. A painting of a forest means nothing to someone who has never seen a forest. A recording of rain sounds like noise unless someone teaches you what rain is. The artifacts need context, they need curation. They need teachers who can explain what they mean and why they matter. Now let's talk about preparing for arrival. Because the ultimate goal of the mission is not just to keep the ship running, it is to reach the destination and establish a colony on a new world. And the generation that arrives, the one that will actually land on the planet and start building a new society, will be the descendants of people who left Earth hundreds of years earlier. They will have no direct experience with planets, no experience with open skies or weather or ecosystems. Everything they know about colonization will come from textbooks and training programs designed by people who are long dead. Training for colonization has to start long before arrival, decades before, maybe a century before. The crew needs to learn how to build habitats on a planetary surface, how to extract resources from soil and rock, how to grow food in open fields rather than hydroponic tanks, how to deal with weather, with gravity that is not artificial, with native life forms, if any exist, with diseases and parasites and environmental hazards that do not exist on the ship. All of this has to be taught theoretically because there is no way to practice it in space. The ship is not a planet. You cannot simulate a thunderstorm or a dust storm or a flood or an earthquake. You cannot prepare people for the feeling of standing on solid ground under an open sky when they have spent their entire lives in a rotating metal cylinder. Some proposals suggest using virtual reality to give the crew a taste of what planetary life will be like. Simulations of walking through forests, swimming in oceans, standing on mountains. That helps, maybe. But virtual reality is still a simulation. The brain knows it is not real, and even the best simulation cannot replicate the physical sensations, the feeling of wind on your face, the smell of soil, the sound of birds or insects or rustling leaves. The crew trained entirely in virtual reality will arrive on the planet and be overwhelmed by the sensory overload. Everything will be new, everything will be unpredictable, and they will have to adapt on the fly or die. The training also has to cover governance and social organization. The ship is a closed hierarchical society with a mission and a command structure. The colony will be something different, open, expanding, with new resources and new challenges and new opportunities for conflict. Who makes decisions? Who owns the land? Who controls the resources? How are disputes resolved? The answers to these questions have to be worked out before the ship arrives, or the colony will tear itself apart within the first generation. And working them out requires teaching political philosophy, history, law, and ethics. The colonists need to understand how societies are built, how they succeed, how they fail, how to avoid the mistakes that destroyed civilizations on Earth. And then there is the knowledge that has to be preserved not for the journey, but for after. Medical knowledge for treating diseases that do not exist on the ship but might exist on the planet. Agricultural knowledge for growing crops in soil rather than hydroponics. Engineering knowledge for building cities and infrastructure. Scientific knowledge for understanding the new world. All of this has to be carried forward, kept alive, passed down, because the colony will not have the resources to rediscover everything from scratch. If the knowledge is lost, the colony starts over at zero. And starting over at zero on an alien world with limited supplies and no support is a death sentence. So the education system on a generation ship is not just about training people to operate the ship. It is about preserving the entirety of human knowledge. Technical, scientific, cultural, historical, philosophical, all of it. and passing it forward intact across centuries, through linguistic drift, through cultural change, through generational turnover, through equipment failures and data loss, and the slow grinding erosion of time. The ship has to function as a university, a library, a museum, and a cultural archive all at once. And it has to do so with a tiny population, limited resources, and no possibility of calling for help. This is the hardest part of a generation ship, not the propulsion, not the life support, not even the psychology. The hardest part is ensuring that the people who arrive at the destination still have the knowledge and the skills and the culture and the purpose to do something with it, to build a new world, to carry forward the legacy of Earth, to justify the sacrifice of all the generations who lived and died in the void without ever seeing the destination. Because if the ship arrives and the descendants are too damaged, too ignorant, too divided, too hopeless to establish a colony, then the entire mission was for nothing. The ship becomes a coffin. The generations who suffered and sacrificed did so for no reason. And the dream of reaching the stars dies in orbit around a planet that will never be home. That is the weight of education on a generation ship. It is not a side project. It is the core, the foundation, the thing that determines whether the mission succeeds or fails, and the people responsible for it, the teachers and the librarians and the archivists and the knowledge keepers, carry a burden as heavy as any engineer or doctor or leader. They are preserving not just information, they are preserving humanity itself. And when the ship finally arrives, when the descendants stand on solid ground for the first time in centuries and look up at an alien sky, the question will not be whether the hull held or the reactor kept running. The question will be whether they still remember who they are, whether they still understand where they came from, whether they still carry the knowledge and the culture and the purpose that make them human. And if the answer is yes, it will be because someone, generations ago, taught them, and someone before that taught the teacher, and the chain held. 400 years, that is how long the ship has been traveling. The engines, if there were engines, have long since gone silent. The vessel is coasting now, drifting through the void at whatever velocity it reached in the early decades of the journey, back when the original crew was still alive, back when Earth was still a memory rather than a myth. The people inside have never known anything but the ship. Their parents did not know Earth. Their grandparents did not know Earth. Earth is a story now, a collection of images and texts and recordings that mean less with every passing generation. The ship is reality. The ship is everything. Except now, for the first time in 4 centuries, something is changing. The stars ahead are getting brighter, one star in particular. And the generation currently alive, the people who have spent their entire lives in the rotating metal cylinder, are about to face a problem their ancestors could only imagine. They have to stop. Deceleration is not optional. The ship is traveling at a significant fraction of the speed of light. Exactly how fast depends on what propulsion system got it up to speed in the first place. But let us assume it is moving at about 10% of light speed. That is roughly 18,600 miles per second. At that velocity, you cross the distance from the Earth to the Moon in about 13 seconds. You are not landing at that speed. You are not even surveying the star system at that speed. If you tried to fly past Proxima Centauri at 10% of light speed, you would scream through the system in a matter of hours and keep going into the dark beyond. The entire mission would be over before anyone had time to identify which planet, if any, was worth approaching. So the ship has to slow down, and slowing down at interstellar velocities is nearly as hard as speeding up in the first place. In fact, it might be harder because you have to do it without destroying the ship or killing everyone inside. The simplest method, in theory, is to flip the ship around and fire the engines in the opposite direction. The same thrust that accelerated you now decelerates you. The problem is that the engines have been off for centuries. They were only needed at the start of the journey to build up speed, and possibly for a few decades of coasting acceleration if the mission profile allowed it. After that, they shut down. Fuel was conserved or exhausted. Components were cannibalized for other repairs. The people currently alive might not even know how to restart the engines because no one has needed to operate them in living memory. That is the first nightmare scenario. The ship arrives at the destination and the crew cannot slow down because the deceleration system, whatever it is, has degraded or failed or been forgotten. The mission ends not with a landing, but with a flyby. The ship passes through the star system, the crew watches the planets drift past the viewports, and then the ship keeps going, forever. There is no turning around, no second chance. The descendants of the original crew spend the rest of their lives, and their children spend their lives, and their children's children, drifting through empty interstellar space with nothing to do and nowhere to go. The ship becomes a tomb in motion. Assuming the deceleration system works, the process still takes years, maybe decades. You cannot slam on the brakes at interstellar speeds. The G-forces would pulverize everyone on board. Deceleration has to be gradual, a slow, sustained burn that chips away at the ship's velocity over a long period of time. During that time, the crew has to prepare. They have to survey the star system. They have to identify planets. They have to analyze atmospheres, surface conditions, magnetic fields, radiation levels. They have to pick a target. And they have to do all of this using instruments that are 4 centuries old, maintained by people whose training is based on manuals written by engineers who died before their great-great-great-grandparents were born. The first thing they will see, assuming the sensors still work, is that the star system is not empty. Proxima Centauri, the closest star to Earth, has at least one confirmed planet, Proxima Centauri b. It is roughly Earth-sized. It orbits in the habitable zone, the region where liquid water can theoretically exist on the surface. That sounds promising until you dig into the details. Proxima Centauri is a red dwarf. It is much smaller and cooler than our Sun. The habitable zone is much closer to the star, which means Proxima Centauri b orbits at a distance of only about 4.6 million miles. For comparison, Mercury, the closest planet to our Sun, orbits at about 36 million miles. Proxima b is 8 times closer to its star than Mercury is to ours. Being that close to a red dwarf comes with problems. The planet is almost certainly tidally locked. One side always faces the star. One side always faces away. The day side is scorched by constant radiation. The night side is frozen in perpetual darkness. If there is any habitable region at all, it is the terminator, the narrow twilight zone between eternal day and eternal night, where the temperature might be survivable. The star itself is unstable. Red dwarfs are known for violent flares that erupt without warning, blasting nearby planets with radiation and charged particles. Proxima Centauri has been observed flaring multiple times. Each flare strips away a bit more of any atmosphere the planet might have. If Proxima b ever had a thick atmosphere, it might be gone by now. If it still has one, it might not last. So the crew arrives after 400 years and realizes the planet they were aiming for is marginal at best. Maybe uninhabitable, maybe lethal. What do? They do not have the fuel to go somewhere else. They do not have the supplies to turn around. They are committed. This is the destination. This is where they land, or this is where they die. The mission planners back on Earth 4 centuries ago knew this. They picked Proxima Centauri b not because it was perfect, but because it was the closest option, the least impossible target. And they sent the ship anyway, hoping the people who arrived would figure it out. Let us assume, for the sake of argument, that the planet is survivable, that there is a terminator region with temperatures in a range humans can tolerate, that there is water, either liquid on the surface or frozen in ice caps that can be melted, that there is some kind of atmosphere, even if it is thin or toxic, because an atmosphere can be processed and improved over time, that there is no native life, or if there is, it is microbial and not immediately lethal. These are enormous assumptions, but without them, there is no story. The ship either lands or everyone dies, so let us say they land. The landing is not gentle. The ship is 36 miles long. It is not designed to enter an atmosphere. It is not aerodynamic. It is a rotating cylinder built in space and meant to stay in space. So the crew does not land the ship, they disassemble it. Or more accurately, they decouple the parts that were always meant to detach. The ship is built in layers, like a Russian nesting doll. The outer shell is structure and shielding. The middle layers are habitats and farms. The innermost core contains the shuttles, small craft that were carried along for the final descent. These shuttles have been sitting in storage for 400 years. No one alive has ever flown one. The manuals say they work. The training simulations say they work. But training simulations are not the same as reality, and the crew is about to find out whether the engineers 4 centuries ago got the design right. The first shuttle detaches. It fires its engines, maneuvers away from the ship, and begins the descent. Inside are a few dozen people. Volunteers, or more likely, people selected by the ship's leadership because they are young, healthy, trained, and expendable. If the shuttle crashes, the mission does not end. There are other shuttles, other people. The first landing is a test, a gamble, and the people inside know it. The descent takes hours. The planet looms larger in the viewports. For the first time in 400 years, human beings are seeing a world from above. Not simulations, not recordings from Earth. A real planet. Real clouds, if there are clouds. Real mountains and valleys and oceans, if there are oceans. The crew is seeing something no one in the ship's history has ever seen outside of a textbook, and they are seeing it through scratched viewports on a shuttle that has not been tested in 4 centuries, falling toward a surface they do not understand. The atmosphere, if there is one, hits hard. The shuttle shakes. Heat builds up on the hull. The crew is strapped in, pressed back into their seats by deceleration forces they have never felt before, because the ship's artificial gravity was constant and smooth and nothing like this. This is violent. This is real. The shuttle is a brick screaming through alien air, and if anything goes wrong, if the heat shield fails, or the guidance system miscalculates, or the parachutes do not deploy, the crew becomes a crater. The parachutes deploy, the shuttle slows, the ground rushes up. And then, with a jolt that rattles teeth and bones and every piece of equipment on board, the shuttle lands. The engines shut down, the shaking stops. For a long moment, no one moves, no one speaks. They are sitting inside a metal box on the surface of an alien world, and they have no idea what is outside. The sensors say the air is breathable, or mostly breathable. The temperature is survivable. The radiation levels are high, but not immediately lethal. The data says they can open the hatch. The data also said the shuttle would work, and it did, barely. So they open the hatch. The first person to step out is someone whose name we will never know. a descendant of the original crew, born on a ship, raised in a rotating cylinder, trained to walk on artificial gravity that was created by spinning metal. They step out onto solid ground for the first time in their life, and the ground does not spin. The gravity is real, planetary gravity, and it feels wrong. Too strong, maybe, or too weak, depending on the planet's mass. Their body, which adapted over generations to the specific forces of the ship, does not know how to process this. Their legs buckle, their balance fails, they fall. This is the first lesson of planetary colonization. Human bodies are adaptable, but adaptation takes time. The crew has spent centuries in an environment that was close to Earth normal, but not quite. The rotation of the ship created artificial gravity, but it was not the same as standing on a planet. The Coriolis effect subtly altered how they moved. The strength of the gravity varied depending on where they were in the ship. Near the axis, it was weaker. Near the outer hull, stronger. Their bodies learned to compensate. Their muscles developed in specific ways. Their bones, their tendons, their sense of balance, all of it calibrated to the ship. Now they are on a planet, and the planet does not care about their calibration. Gravity is uniform. It pulls straight down, always, everywhere, with no variation. Walking feels strange. Running feels dangerous. The crew stumbles, they fall, they get back up and try again. Over days and weeks, they adapt. The young adapt faster, the old adapt slower. Some never adapt. They spend the rest of their lives unsteady, always feeling like the ground is shifting beneath them, even though it is not. The planet is solid. They are the ones who are broken. Then there is the air. The sensors said it was breathable, but breathable is not the same as comfortable. The atmosphere is thin, maybe, or too thick. The oxygen concentration is slightly off. The pressure is wrong. Breathing takes effort. Some people hyperventilate, others feel like they are suffocating. The body adjusts, but the adjustment is not pleasant. Headaches, dizziness, fatigue. For weeks, maybe months, the crew feels sick. Not dying, but not well, just constantly wrong. And then there is the sky. For 400 years, the crew looked up and saw a metal ceiling. Or if they looked out a viewport, they saw black, empty space, distant stars. Now they look up and see something else, maybe clouds, maybe a glowing band of light from a nearby gas giant, if the planet is a moon. Maybe the star, Proxima Centauri, hanging in the sky, dimmer and redder than the sun they have only ever seen in recordings. The sky is alien. It is too big, too open. There is no ceiling, no boundary. The horizon stretches away in every direction, and there is nothing to stop it. Some of the crew, the ones who grew up in enclosed spaces, cannot handle it. They panic. They retreat back into the shuttle. They refuse to go outside. The term for this is agoraphobia, fear of open spaces. On Earth, it is a disorder. On a generation ship turned planetary colony, it is an epidemic. The crew that does venture out starts surveying. They need water. They need food. They need shelter. The shuttles are not permanent homes. They are transport vehicles. Small, cramped, not designed for long-term habitation. The crew needs to build structures. They need to set up farms. They need to establish infrastructure. And they need to do all of this on a planet they do not understand, using skills they have never practiced outside of simulations. The soil, if there is soil, is not Earth soil. It might be rock, it might be dust. It might be chemically hostile, full of perchlorates, or heavy metals or compounds that poison plants. The crew tests it. They try to grow crops. Some crops fail immediately, others grow stunted and sickly. A few maybe survive. The crew eats what they can grow and rations what they brought from the ship. They are hungry, constantly. The hydroponic farms on the ship produced reliable yields because the environment was controlled. The environment on the planet is not controlled. It is chaotic. There are storms if there is weather. Temperature swings between day and night if the planet rotates. Dust storms if the atmosphere is thin and the surface is dry. Every one of these variables kills crops and stresses the crew. Then there is the radiation. Proxima Centauri is a flare star. Every few days or weeks it erupts. The surface of the planet is blasted with X-rays and ultraviolet light. The crew, already weakened by the transition to planetary life, is now being irradiated. They build shelters underground or pile rocks on top of their structures for shielding. They wear protective suits when they go outside. They huddle in bunkers during flares. Radiation sickness becomes common. Cancer rates climb. The colony is surviving, but it is not thriving. And all of this assumes the planet is uninhabited, that there is no native life. Because if there is native life, even microbial life, the crew has a new problem: compatibility. Life on Earth is built on a specific chemistry: DNA, RNA, proteins made from 20 amino acids, sugars and lipids, and all the molecular machinery that evolved over billions of years in Earth's oceans. Life on another planet, if it evolved independently, would almost certainly use different chemistry, different molecules, different building blocks. The odds that alien life would be directly compatible with human biology are essentially zero. That cuts both ways. Alien microbes probably cannot infect humans because they are not adapted to human biochemistry. But humans also cannot eat alien organisms because the molecules are wrong. The proteins do not break down into usable amino acids. The sugars do not metabolize. Eating alien life is like eating plastic. It fills your stomach, but provides no nutrition. The crew brought seeds and livestock embryos from the ship, but if those fail, if the crops do not grow and the animals do not survive, the crew cannot fall back on hunting or foraging. The planet might be covered in life, and all of it is inedible. Now add the ethical problem. If the planet has life, even simple life, does humanity have the right to colonize it, to terraform it, to wipe out native ecosystems and replace them with Earth species? The mission planners 4 centuries ago did not worry about this. They were sending a ship to save humanity. The survival of the species took precedence over everything else. But the crew standing on the surface of the planet, looking at alien organisms under a microscope, might feel differently. They might argue that they have no right to destroy a biosphere that took billions of years to evolve. That even microbial life has value. That colonization is conquest, and conquest is wrong. Other members of the crew will disagree. They will point out that they traveled 25 trillion miles and spent 400 years in a metal tube to get here. That they have no other options. That Earth is gone, or might as well be, because there is no going back. That survival justifies any action. The colony fractures. Some want to minimize the impact on native life. Others want to terraform aggressively, to turn the planet into a second Earth, regardless of the cost. The debate becomes a conflict. The conflict becomes violence. The colony, already struggling with radiation and crop failures and psychological collapse, now tears itself apart over a philosophical question that has no clear answer. Let us assume the colony survives the initial decades, that enough crops grow, that enough shelters are built, that the population stabilizes. The people who landed are aging now. They are the transition generation, the ones who remember the ship. Their children, born on the planet, are something new. They are the first generation of humans in 400 years to grow up under an open sky. They do not remember the ship except as stories. To them, the ship is the abstraction, the planet is reality, and they are different, not just culturally, physically. Their bones develop in real gravity. Their muscles adapt to planetary conditions. Their lungs adapt to the atmosphere. Their skin adapts to the radiation. Over generations, the colonists diverge from the humans who left Earth. They are taller, maybe, or shorter, depending on the gravity. Their skin is darker, maybe, or paler, depending on the radiation and the star's spectrum. Their cardiovascular systems are stronger or weaker. Their eyes, adapted to the dimmer red light of Proxima Centauri, might struggle to see blue wavelengths that were common under Earth's sun. They are still human, but they are not the same kind of human. This is the final transformation. The people who left Earth were Homo sapiens. The people who arrive after 400 years in space and generations on an alien world are something else. Not a new species, not yet, but the beginning of one. A branch of humanity shaped by an environment that no human was designed for. They carry the genetic legacy of Earth, but they are no longer Earthlings. They are Proximans, or whatever name they choose for themselves. And if they ever encounter humans from Earth again, if another ship arrives centuries later, the two populations might barely recognize each other. The colony grows, slowly, painfully, with setbacks and losses and tragedies that would have ended the mission if the crew had any other choice. But they do not. This planet, hostile and alien as it is home now, the only home they will ever have. The ship, if it still orbits above, is a relic, a monument to the journey. Some colonists propose dismantling it for materials. Others want to preserve it as a museum. The debate is bitter because the ship represents different things to different people. To the older generation, it is sacred, the vessel that carried them across the void. To the younger generation, it is irrelevant, a hunk of metal that has nothing to do with their lives. Eventually, the ship is abandoned. It drifts in orbit, a silent tomb full of empty corridors and dead systems. Decades later, it falls. The orbit decays. The ship re-enters the atmosphere, breaks apart, and burns. Pieces of it rain down across the planet, scattering across continents that are just beginning to be named. The colonists watch the sky and see streaks of light, shooting stars, the funeral pyre of the generation ship. The end of one era and the beginning of another. And now the colony faces a question that the original mission planners never had to answer. What happens next? The colony exists. Humanity has a foothold on another world, but the foothold is fragile. The population is small. The resources are limited. The planet is hostile. And there is no plan for what comes after survival. Do they expand? Do they build cities? Do they try to terraform the planet into something more like Earth? Do they adapt further, using genetic engineering or selective breeding to become even better suited to the environment? Do they reach out, somehow, back to Earth, assuming Earth still exists and anyone there still cares? Or do they simply endure, generation after generation, holding on, surviving, never quite thriving but never quite dying? A human colony on an alien world, cut off from the rest of the species, slowly becoming something new, something strange, something that started as an ark, carrying the hope of humanity, and ended as a seed planted in foreign soil, growing into a tree that bears fruit no one on Earth would recognize. That is the arrival. Not a triumphant landing, not a victory. Just the brutal, grinding reality of stepping off a ship after 400 years and trying to live on a world that does not want you there. The people who arrive are not the people who left. The world they find is not the world they imagined, and the future they build, if they build one at all, is not the future anyone planned for. It is the future that was forced on them by distance and time and the unforgiving physics of interstellar travel. And whether that future was worth the cost, whether the generations who suffered and died in the void would look at their descendants and feel pride or horror, is a question that can never be answered. Because the people who would have to answer it are 25 trillion miles away and 400 years in the past. All that remains is the colony, the altered humans, the foreign home, and the question of what they do next. The ship burned in the atmosphere and scattered itself across a planet that will never be called Earth. The colonists watched the streaks of light, the funeral pyre of the vessel that carried their ancestors across 25 trillion miles of nothing, and then they went back to work. Because there was work to do. There is always work to do. The farms need tending, the shelters need reinforcing. The water recyclers, cobbled together from ship components and local materials, need constant monitoring. The children need teaching, the sick need care. And somewhere in the back of everyone's mind sits the same question that has sat there since the day the first shuttle landed. Was it worth it? That question does not have an easy answer. It might not have an answer at all. Because the people standing on that alien world, breathing thin air under a dim red star, are not the people who made the choice to leave Earth. They are not the people who designed the mission or built the ship or volunteered to board it, knowing they would die in transit. They are the descendants. The inheritors of a decision made 400 years ago by strangers whose names they barely remember and whose motivations they can only guess at. They are living out the consequences of a choice they never made, in a place they never asked to be, for a purpose that was supposed to matter but feels increasingly abstract with every passing generation. So let's go back to the beginning, back to Earth. Back to the moment when someone, somewhere, looked up at the stars and decided that humanity needed to leave. Not just explore, not just visit, leave, permanently. Build ships large enough to carry thousands of people and everything they would need to survive for centuries. Aim those ships at distant stars and launch them into the void with no realistic chance of return. That decision, that choice to build generation ships and send them out into the galaxy, is one of the most audacious ideas our species has ever seriously considered. It is also one of the most brutal. The concept rests on a foundation of staggering optimism and equally staggering desperation. The optimism says that humanity is capable of engineering closed-loop ecosystems stable enough to function for centuries, that we can design social structures resilient enough to survive generational turnover without collapsing into chaos, that we can preserve knowledge across hundreds of years in a sealed environment with no outside input, that we can raise children in confinement and convince them to raise their own children in confinement and keep that cycle going for 10 or 20 or 30 generations until someone, someday, steps onto solid ground. The optimism says we can do all of that because we have to, because the alternative is extinction or stagnation or watching our species die slowly on a single planet as resources dwindle and opportunities slip away. The desperation says the same thing, but with a different tone. The desperation says we have no choice, that Earth is finite, that disasters, natural or man-made, will eventually render the planet uninhabitable, that putting all of humanity's eggs in one planetary basket is a gamble we cannot afford to keep making, that the only way to ensure long-term survival is to spread out, to become a multi-world species, to plant seeds on other planets, so that if Earth dies, humanity does not. And if the only way to do that with the physics we understand is to build generation ships and send people on journeys they will never complete, then that is what we do. Because the alternative is worse. Both of those perspectives, the optimism and the desperation, are built on the same unstated assumption, that the future matters more than the present. That the survival of the species as an abstract concept justifies the suffering of individuals, that it is acceptable, even noble, to sacrifice the happiness and freedom of living, breathing human beings if it means their distant descendants might have a chance at something better. That assumption is not self-evident, it is not universally accepted, and it is the root of every ethical problem with generation ships. Let's be very clear about what we are asking people to do. We are asking the original crew to board a ship, knowing they will spend the rest of their lives confined to a metal cylinder, knowing they will never see the destination, knowing their children will not see it either, knowing that the entire purpose of their existence, from the moment they step on board, is to serve as a biological link in a chain that stretches across centuries. They are not colonists, they are not explorers, they are custodians. Their job is to keep the ship running and keep the population alive long enough to pass the mission to the next generation. That is it. That is their entire life. The original crew, at least, volunteers for this. They make a choice. They sign up knowing what they are getting into, or at least knowing as much as anyone can know about a situation no one has ever experienced. They believe the mission is worth it. They accept the sacrifice. Whether that acceptance is informed consent or self-deception or desperation or idealism is debatable, but at least it is theirs. They chose. Their children do not choose. The second generation is born on the ship. They grow up in an environment they did not ask for, serving a mission they had no part in designing, for the benefit of people who will not exist for hundreds of years. They inherit their parents' purpose second-hand, and with every passing generation, that purpose becomes more diluted, more abstract, harder to believe in. By the time you reach the 5th or 10th generation, the mission is not a living goal. It is a tradition, a story, a set of rules handed down from ancestors who are long dead and whose reasons for doing any of this are increasingly incomprehensible to people who have only ever known the ship. And yet the mission demands that every generation sacrifice just as much as the first. They have to maintain the systems. They have to grow the food. They have to raise the children. They have to pass on the knowledge. They have to endure confinement and psychological strain and social dysfunction and the crushing weight of living in a sealed box with no escape. They have to do all of that not for their own benefit, but for the benefit of descendants they will never meet. People who will be born centuries after they die. People who might hate them for making the choices they made, or resent them for perpetuating a mission that should have been abandoned generations ago. That is the bargain. That is what a generation ship demands. And the question is not whether it is technically possible. The question is whether it is morally defensible, whether we have the right to impose that burden on people who never consented to it, whether the promise of a distant future justifies the suffering of countless individuals in the present. There is no easy answer. Some will argue that yes, it is justified, that the survival of the species outweighs individual autonomy, that the people born on the ship are not slaves because they are free to make choices within the constraints of their environment, even if they cannot choose to leave, that the mission once started creates its own moral imperative because stopping it means condemning everyone on board to a pointless death, that the descendants, when they finally arrive, will look back at their ancestors and feel gratitude rather than anger, because without those sacrifices, they would not exist. Others will argue that no, it is not justified, that consent cannot be inherited, That being born into a situation you cannot escape is functionally identical to imprisonment, regardless of how you frame it. That the mission is a form of multi-generational coercion, where each generation is held hostage by the choices of the one before it. That even if the descendants are grateful, gratitude does not retroactively make the suffering ethical. That the ends do not justify the means, no matter how grand the ends or how desperate the circumstances. Both positions are internally consistent, both are defensible, and both are ultimately matters of values rather than facts. You cannot prove one side right and the other wrong, because the debate is not about what is true, it is about what is acceptable, about where you draw the line between collective survival and individual rights, about whether you believe the future is worth more than the present, or whether you believe that every human being, regardless of when or where they are born, has an equal claim to autonomy and happiness. What makes the debate even harder is that it is not hypothetical. If we ever build a generation ship, real people will face these questions. Real children will be born into confinement. Real adults will spend their lives serving a mission they did not choose. Real societies will fracture under the strain. And real consequences, irreversible and permanent, will follow from the decisions made by mission planners who will be dead long before the full impact of those decisions becomes clear. Now let's talk about what happens if the mission succeeds, if the ship arrives, if the colonists land, if they manage to establish a foothold on an alien world and survive long enough to build something resembling a stable society. Was it worth it then? Does success retroactively justify the cost? The answer depends on who you ask. The colonists themselves, the ones standing on the surface of the new world, might say yes, they exist because the mission succeeded. Their children will grow up under an open sky instead of a metal ceiling. Humanity has a second home, a backup in case Earth fails. The species is safer, the future is more secure. From their perspective, the sacrifices of their ancestors, as brutal as they were, made all of this possible. Of course it was worth it, but the people who paid the cost are not around to answer. The generations who lived and died in the void, who never saw the destination, who spent their entire lives in confinement for the sake of a future they could not experience, they do not get a vote. We cannot ask them whether it was worth it, because they are gone, and the people who benefit from their sacrifice, the descendants who inherit the new world, are not the ones who suffered, so their gratitude, while genuine, does not actually settle the question, it just shifts it. Let's try a different angle. Forget ethics for a moment and focus on practicality. Even if we accept that generation ships are morally justifiable, are they actually the best option? Are they the most efficient way to spread humanity across the stars, or are they a desperate fallback plan born out of the limitations of our current technology? The answer, almost certainly, is the latter. Generation ships are what you build when you cannot build something better. If we had faster propulsion, if we could reach another star in a decade or two instead of centuries, we would not need generation ships. The original crew would live to see the destination. The psychological burden would be manageable. The social stability problems would shrink. If we had cryogenic suspension that actually worked, if we could freeze people at the start of the journey and wake them up at the end, we would not need generation ships. There would be no generational turnover, no knowledge decay, no cultural drift. The people who left Earth would be the people who arrived. If we had some kind of breakthrough in physics, if we discovered a way to bend space or travel faster than light or open wormholes, generation ships would become obsolete overnight. We could send colonists to distant stars the way we currently send people to other continents, quickly, safely, without requiring multi-generational commitment. The fact that we are even discussing generation ships is a confession of failure, a recognition that with the physics we understand, interstellar travel is so hard and so slow that we have to resort to measures that border on inhumane just to make it possible at all. So generation ships are not the dream, they are the compromise, the fallback. The thing we might have to do if we run out of time before we figure out something better. And that raises another uncomfortable question. If we build a generation ship and send it out, and then 100 years later we invent faster propulsion and send a second ship that overtakes the first, what do we tell the people on the original ship? That their ancestors suffered for nothing? That the mission they have been perpetuating for generations is now pointless because a newer, faster ship is going to arrive first? This is not a hypothetical problem. It is a real risk. Technology improves. What seems impossible today might be routine in 50 years. If we commit to a generation ship, we are locking in the technology of the present for a mission that will last centuries. And there is a very real chance that by the time the ship arrives, the destination will already be colonized by people who left Earth decades or even centuries after the generation ship launched, but got there faster because they had better engines. That is the paradox of long-duration missions. The longer the mission takes, the more likely it is that someone else will find a faster way to do the same thing and make your effort obsolete. It is not an argument against trying. It is just a reminder that generation ships are not a solution. They are a gamble. A bet that the mission will succeed before it becomes irrelevant. And the people making that bet are gambling with lives that are not their own. Now let's talk about legacy. Because even if the mission succeeds, even if the colonists arrive and thrive, the legacy of a generation ship is complicated. The people who benefit are not the people who paid the cost. The people who are remembered are not the people who did most of the work. History, when it is written by the colonists, will focus on the founders, the visionaries who designed the mission, the leaders who made the hard decisions, the first generation who boarded the ship and set the whole thing in motion. They get the monuments, they get the holidays, they get their names etched into stone and their stories told to children. The middle generations, the ones who spent their entire lives maintaining systems and raising children and passing on knowledge in the void, they fade into obscurity. They were not founders, they were not arrivals, they were transitions, anonymous links in a chain. Their names might be recorded in a database somewhere, but no one remembers them, no one tells their stories. They are footnotes. And that is, if the mission succeeds. If it fails, they are not even that. They are just people who died in space for no reason. That is the brutality of the generation ship concept. It asks people to sacrifice everything for a future they will never see and offers them nothing in return except the abstract knowledge that they are part of something larger. Maybe that is enough for some people. Maybe the idea of contributing to the survival of the species is its own reward. But it is worth acknowledging that the reward is intangible, the cost is immense, and the people paying the cost have no way to opt out. So where does that leave us? What is the enduring legacy of the generation ship idea? Is it a testament to human resilience and ingenuity, a symbol of our willingness to sacrifice for the greater good? Or is it a monument to hubris, a plan so ambitious and so flawed that it exposes the limits of what we can reasonably ask of ourselves and each other? The answer is probably both. The generation ship concept captures something fundamental about humanity: our refusal to accept limits, our insistence that the future can be better than the present if we are willing to work for it, our belief that survival, even survival on the most brutal terms imaginable, is better than extinction. Those are admirable traits. They are the traits that got us out of the caves and across the oceans and into space in the first place. They are also the traits that have led us into countless disasters throughout history. Ambitious projects that sounded brilliant on paper and turned into nightmares in execution. Grand visions that ignored the human cost until it was too late. A generation ship is both of those things at once. It is humanity at its best and humanity at its worst. It is the dream of reaching the stars and the willingness to sacrifice anything to get there. It is optimism and desperation wrapped together so tightly you cannot separate them. And it is a question that we have not answered yet and might never answer. Are we willing to pay the price? Are we willing to ask others to pay it for us? And if we do, if we build the ships and launch them and send generations of people into the void, will the people who arrive look back and call us heroes or monsters? The only certainty is this: if we ever build a generation ship, the people who board it at the start of the journey will not be the people who step off at the end. The ship will carry human beings, yes, but it will transform them physically, psychologically, culturally, genetically. The humans who arrive will not be the humans who left. They will be something new, something shaped by 400 years of confinement and adaptation and isolation. They will carry our DNA, but they will not carry our world. Earth will be a memory, and then a story, and then a myth. The planet they land on will become their home, not because they chose it, but because they have no other choice. And maybe that is the real legacy of the generation ship. Not the technology, not the engineering, not even the survival of the species. The legacy is the transformation. The proof that humanity can endure almost anything if the stakes are high enough. That we can adapt to environments we were never designed for. That we can sacrifice the present for the future and keep going even when the future is so far away it might as well be imaginary. That we can look at a distance like 25 trillion miles and say, yes, we will cross it, no matter how long it takes, no matter what it costs, because the alternative is to give up. And giving up is not in our nature. The generation ship is a bet on that nature. A bet that the drive to survive, to spread, to reach beyond what is known, is strong enough to sustain people through centuries of hardship. That hope, even hope for a future you will never see, is powerful enough to justify a life spent in confinement. That legacy, the chain of hands passing knowledge and purpose forward across generations, is worth the cost. Whether that bet pays off, we do not know yet. We will not know for centuries, if we ever know at all. But the bet itself, the willingness to even consider something as audacious and terrible and necessary as a generation ship, says something about who we are. It says we are not content to stay in one place. It says we believe the future can be saved, even if we cannot be part of it. It says we are willing to build bridges we will never cross, and plant trees we will never sit under, because someone, someday, will cross those bridges and sit under those trees, and that is enough. That is the enduring legacy. Not the ships themselves, which might never be built. Not the destinations, which might never be reached. The legacy is the idea, the refusal to accept that 25 trillion miles is too far. The insistence that if the only way forward is to send our children into the void and trust that their children will carry the mission forward, then that is what we do. Because the void is vast and cold and indifferent, but humanity is stubborn, and sometimes stubbornness is enough. The ship burned in the atmosphere. The colonists watched, and then they went back to work. Because the journey is over, but the mission is not. It never ends, it just changes. From survival in the void to survival on a foreign world, from maintaining a ship to building a civilization, from inheriting a purpose to defining one. The generation ship brought them here, but it cannot tell them what to do next. That is their choice now, the first choice any of them have ever really had. And maybe that is the point. Maybe the entire brutal, centuries-long journey was not about reaching a destination. It was about creating a future where choice is possible again, where people can look up at an alien sky and decide for themselves what comes next, where the chains of inherited purpose finally break and the descendants of the void become the architects of their own lives. If that is true, if the suffering of the middle generations bought freedom for the final one, then maybe it was worth it. Not because the cost was acceptable, it never will be, but because the alternative, the slow death of a species trapped on a single world with no future and no hope, is worse. The generation ship is not a solution, it is a last resort, a desperate, flawed, deeply human attempt to survive against impossible odds. And if we ever build one, the people who board it will carry with them not just the tools and knowledge needed to reach another star, but the weight of every choice we made and every choice we failed to make. They will carry our hope and our guilt in equal measure. And when they arrive, if they arrive, they will have to decide whether it was worth it. We will not be there to answer. We will be 25 trillion miles and 400 years behind them, dust on a planet they will never see, remembered only in stories that grow dimmer with every generation. That is the price, that is the legacy, that is the future forged in the void. The ship is gone, the journey is over, and standing on the surface of an alien world under a dim red star, the descendants of people who left Earth 4 centuries ago are finally free to ask a question their ancestors never could. What now? That question matters more than the engineering, more than the propulsion systems or the closed-loop ecosystems or the genetic diversity calculations, because the real legacy of a generation ship is not the vessel itself, it is the people it transforms. Human beings who spent lifetimes crossing a distance so vast that light itself takes years to bridge it, who endured confinement and psychological strain and the crushing weight of purpose they never chose, who kept knowledge alive across centuries, who raised children in the dark and taught them to raise their own children, generation after generation, for a destination none of them would ever see. They did the impossible, not because it was easy or fair or even humane. They did it because the alternative was extinction. Because humanity looked at the stars and decided that 25 trillion miles was not too far. That the future, even a future bought with the suffering of countless individuals, was worth fighting for. That hope, no matter how abstract or distant, was powerful enough to sustain life in the void. Whether that makes us brave or foolish is not for us to decide. We are not the ones who will pay the price. The people who board a generation ship, if we ever build one, will make that judgment. And the descendants who arrive, standing on ground their ancestors never imagined, will make it again. They will look back across the centuries at the chain of hands that carried them forward, and they will ask the same question we are asking now. Was it worth it? We will never hear their answer. We will be dust by then, but the question will remain, echoing